Hello there, and welcome to Science for Sleep, where the pace slows down enough for wandering thoughts to settle, and where questions about the universe can drift into a comfortable corner of your mind without demanding any urgency from you. Tonight, we're easing into a subject that has shaped every step you've ever taken, every breath you've ever pulled into your lungs, and every moment the ground has quietly held you without asking for thanks. We're moving toward the idea that the force we've trusted since the day we were born might not be what we think it is at all. Gravity feels simple when you drop a pen, or stretch out on a bed, or watch steam rise from a mug. But the more scientists investigate it, the less it behaves like a friendly, predictable rule, and the more it looks like a story missing a few important pages. While we settle into this question together, I'd love to know where you happen to be listening from tonight. Maybe you're in a familiar room with dim lights, or somewhere new where the sounds settle differently against the walls. And as you're sitting or lying there, what time is it in your part of the world right now? Those small details somehow create a calm starting point, a shared moment, even in a topic as large as this one. If you find this gentle science exploration soothing, or if it helps your mind unwind while the day loosens its grip, you're welcome to like this video or subscribe to keep this quiet corner growing. And now, we'll ease forward, letting the question unfold slowly without rushing toward any dramatic conclusions, just letting one idea open into the next as naturally as a breath. You might think there's nothing mysterious about the pull that keeps your feet on the ground. The idea that objects fall, that things stay anchored unless lifted, feels almost too basic to question. Yet once you begin to look at how gravity behaves across different scales, the confidence starts to wobble a little. Something that felt obvious begins to look more like a convenient explanation than a complete one. When a small object drops from your hand, it lands just where you expect. When a tossed ball arcs through the air, the path is smooth and predictable. But once you stretch your view far beyond the familiar range of human experience, the rules seem to loosen. Stars hold their planets with surprising steadiness. Galaxies whirl with more speed than should be possible. Clusters of galaxies cling together as if something unseen is reinforcing the bonds. The ground beneath us pulls, yes, but the cosmos behaves as if there are additional hands guiding the motion of everything. Even before telescopes revealed distant patterns, people sensed that gravity was worth trying to understand. Every falling apple, every tide, every orbit carried a message that something important was shaping motion. Early explanations tended to treat gravity as a simple attraction, a pull between objects. The idea seemed so natural that it became the default for centuries. Yet even in those early efforts, small inconsistencies appeared. Objects didn't fall at exactly the same rate in every environment. Celestial motions hinted at details that didn't fully match predictions. Instead of dismissing these quirks, thinkers kept refining their models, trying to reach something that accounted for all of it. The process was slow, layered, and full of revisions, but the belief remained steady that gravity was a force you could define neatly. When the ground holds you in place, you don't feel pulled, you feel supported, almost as though the earth is simply waiting beneath you. The sensation doesn't hint at invisible strings tugging downward. It feels more like a stable arrangement you can rely on. This everyday experience contrasts sharply with the way scientists describe gravity in equations. There, gravity is treated as a universal interaction, affecting all masses at all distances. Yet the gap between what we feel and what the math suggests has grown wider over time. As observations improve, the models stretch further, gaining complexity without gaining clarity. The sense emerges that gravity may not be a simple pull between masses. It might be something that emerges from deeper structures of space, or from relationships we don't yet fully understand. This uncertainty becomes even more pronounced when you shift your attention from falling objects to the behavior of planets and stars. When astronomers track the motions of planets in our solar system, the paths are mostly consistent with traditional explanations, though even here, small deviations required adjustments. But once they started examining galaxies, they noticed something that didn't fit the established laws. Stars were orbiting far too quickly to be held together by the visible mass alone. If gravity worked exactly the way the familiar equations predicted, many galaxies should have torn themselves apart long ago. Instead, they remain intact, spinning with ease as if some additional influence is anchoring their motion. This wasn't a rare exception. It happened everywhere scientists looked, turning a local issue into a universal puzzle. This missing piece encouraged hypotheses that tried to preserve the existing framework rather than overturn it. One of the first major ideas was that there must be more matter present than we could see. Something transparent, not interacting with light, but adding mass in all the right places to strengthen the gravitational pull. The idea solved many equations neatly, so it became widely accepted, even though no one has detected this invisible matter directly. It's a reasonable patch, but a patch nonetheless. The fact that such a massive ingredient remains invisible and unconfirmed feeds the suspicion that perhaps the equations are incomplete, rather than the universe being full of something we just haven't identified yet. If you go back to the surface beneath you, the ground doesn't offer clues that gravity may be misunderstood. It behaves consistently in daily life, allowing us to predict motion with confidence. But the universe doesn't seem content with simplicity. On the scale of galaxy clusters, the patterns become even harder to explain. These enormous groups of galaxies cling together with a strength that defies calculations based on visible mass. The expected motion would cause them to drift apart, yet they remain bound as if tied together by something stronger than anticipated. The conclusion for many scientists became that an additional substance must be present, not only in galaxies, but between them. Still unseen, still theoretical, yet treated as essential to keep the models coherent. This approach carries a quiet assumption, though often unspoken. It assumes the framework we're using must be right, and that any mismatch with observations should be addressed by adding new components rather than questioning the structure itself. But what if the missing ingredient isn't matter at all? What if the way we describe gravity is only a partial story? That question may sound bold, but it's gaining attention as more evidence refuses to sit comfortably within the traditional explanations. The tension grows further when you consider the expanding universe. Observations of distant galaxies reveal that not only is the universe expanding, it's accelerating. If gravity worked strictly as a predictable pull, expansion should slow over time as mass draws everything inward. Instead, galaxies are drifting apart faster than before, as though something is counteracting gravity on the larger scales. Once again, instead of questioning the nature of gravity first, scientists introduce the idea of a force or energy pervading space, driving expansion outward. It fits observations neatly, but like other additions, it lacks direct detection. The pattern continues. Rather than adjusting the core understanding of gravity, new components are added to hold the system together. As you reflect on this growing list of uncertainties, the pull of gravity inside your room remains uncomplicated. The surface beneath you is reliable. The objects around you behave predictably. Nothing in your immediate surroundings suggests the universe should be difficult to explain, yet that contrast reinforces a point often overlooked. The familiar behaviour we see on Earth represents only a small portion of gravity's domain. Once you step beyond that sphere, the rules shift. They don't break completely, but they become harder to fit into the same tidy mould. That's where the curiosity deepens. If gravity behaves differently across different scales, perhaps the explanation should change with it, rather than forcing all observations to align with a single interpretation. You may even find yourself wondering why we cling so tightly to the current model. Part of the reason is that it works exceptionally well for many problems. Engineers, astronomers, and physicists rely on it every day to calculate trajectories, manage satellites, and understand planetary motion. But usefulness does not guarantee completeness. A map can guide you well through familiar territory while still omitting entire regions. The question is whether we're using a map that describes only part of the landscape, and assuming it must apply everywhere. Gravity often slips into the background of your awareness, doing its work without ceremony, offering no hint that something this steady might be hiding complicated truths beneath its surface. After spending time with the idea that the force we trust might be incomplete, it becomes easier to examine the quiet ways it influences everything without ever drawing attention to itself. You can move through an entire day without once considering why your feet stay planted on the ground, or why objects fall instead of floating off in unpredictable directions. The familiarity creates the illusion that we understand gravity deeply, almost instinctively. Yet when people first tried to describe it formally, they didn't do so from a position of certainty. They began with the same quiet confidence you feel when watching something drop, but the more they investigated, the more surprises they encountered. The pattern continues even now, as each technological advancement pulls another curtain back and leaves us questioning again whether the rules we rely on are only fragments of a larger picture. If you pause for a moment and think of the last time you dropped something, a set of keys, a towel, maybe a book, the motion probably felt simple. The object left your hand, moved downward, and settled somewhere predictable. But that simple experience masks what the earliest thinkers had to wrestle with. They didn't know why things fell or why the pull seemed universal. They didn't have a clear way to separate the falling of a stone from the movement of the moon, or the gentle tug of the tides. In fact, much of what they observed seemed unrelated at first, scattered pieces of a puzzle that didn't look like they belonged to the same box. When a stone dropped toward the ground, it looked nothing like the way celestial bodies moved. The motions appeared unrelated until someone took the risk of imagining that perhaps they were linked by the same underlying principle. Even then, the explanation was built on assumptions that felt natural but were never actually confirmed. Once formal laws were established, gravity became easier to describe and predict. Objects followed paths that matched calculations, planets moved in ways that aligned with equations, and the system seemed to settle into something manageable. That quiet reliability encouraged the belief that gravity had been understood well enough, and that everything else science uncovered would simply refine the details rather than overturn the foundation. But what made the system persuasive wasn't that it answered every question. It was that it worked for the problems people could see at the time. When you live in a world where observations are limited to what your eyes and tools can capture nearby, the confidence feels earned. Yet history has shown again and again that theories tend to hold steady until someone looks at a different scale or examines a phenomenon that doesn't fit the earlier assumptions. Gravity followed that pattern closely. As the ability to observe distant regions of space improved, the behavior of gravity began to show deviations from what had been expected. The equations that once seemed universal started requiring adjustments, and eventually those adjustments turned into entire layers of additional hypotheses. For a long time, scientists didn't question the core idea of gravity as a simple attractive force. They simply imposed new elements on top of the existing framework. Some of those additions worked for a while, smoothing out inconsistencies in specific scenarios. Others opened more questions than they answered. The process became less about refining a cohesive theory and more about attaching new explanations to keep the original intact. That doesn't necessarily mean the original was wrong, but it does raise the possibility that it was incomplete in ways that weren't obvious at first. You don't feel any of this complexity when you stand still. The ground feels solid, the air feels still, and gravity feels like a constant quiet companion. That sensation is part of what misleads us. Because gravity doesn't fluctuate in daily life the way other forces might, it gives the impression of being fundamentally understood. Yet the quietness of the force says nothing about its nature. Sound doesn't accompany the embedding of an object in space, nor does any sensation hint that space itself might be curving or stretching. Gravity acts without sensory fanfare, and that makes it harder to recognize when something in the explanation is missing. Once people began to realize that gravity might not behave uniformly across all scales, old assumptions became harder to defend. The force that directs the motion of objects near the ground might not reflect the entire story. The same equations can handle the fall of a small object in the orbit of a planet, but their limits appear when the system widens to include galaxies. Suddenly the expected speeds don't match what's observed. The mass we see doesn't produce the forces we measure. The more the data accumulated, the more gravity began to look less like a simple rule and more like a placeholder for a deeper phenomenon. Some researchers embrace the idea that the missing puzzle pieces must exist somewhere, waiting to be detected. If gravity didn't behave as expected, perhaps something invisible was contributing. It wasn't unreasonable. Science has a long history of discovering previously unknown elements that later became essential parts of well-established theories. But this approach relied on a subtle assumption, the idea that the equations themselves were correct, and the universe was the part that needed adjusting. For a while, this perspective held. It's easier to imagine that the universe contains unseen elements than to believe that the framework tying centuries of observations together might require a fundamental change. But over time, the number of unseen elements required to preserve the original explanation kept growing. More mass needed to be added to galaxies, then more mass between galaxies. Forces had to be introduced not just to account for motion that seemed too strong, but also to explain motion that seemed too weak. Something had to push the universe outward. Something else had to hold structures together. Each of these additions worked mathematically, but together they turned the once elegant model into something more complicated. That shift encouraged a new kind of question. What if the force we've been describing isn't acting the way we assumed, and the missing components are symptoms of a deeper misunderstanding? This idea doesn't undermine the usefulness of existing equations. They describe many situations extremely well. Satellites operate reliably, planetary orbits remain predictable. Engineers rely on gravitational calculations every day to design countless structures. Yet those practical successes don't eliminate the growing number of inconsistencies on larger scales. That contrast between precise predictability and broad uncertainty makes gravity one of the strangest forces we work with. It never stops affecting us, yet we don't truly know what it is. The more scientists examine it, the less it fits neatly into any category. The tension becomes clearer when we consider how gravity compares to the other fundamental interactions. Most forces have measurable carriers or quantifiable behaviours that make them easier to define. Gravity stands apart. It doesn't have the same defined particles, and it doesn't integrate smoothly into the same theoretical framework that unites the other forces. While those interactions behave predictably under extreme conditions, gravity often refuses to cooperate. This mismatch suggests that our understanding of it might not just be incomplete, it might be resting on assumptions that need to be revisited altogether. Even with these concerns, gravity still presents itself as something familiar in everyday life. That familiarity is what makes the deeper questions feel surprising. How can something so steady hide so many uncertainties? The answer lies in the fact that daily experiences represent only a tiny slice of what gravity influences. If you judge a system solely by the part you encounter most often, you risk missing everything that falls outside that narrow range. This isn't a flaw in human perception. It's a natural consequence of how we experience the world. But science depends on looking beyond the familiar, and when it does, it becomes harder to assume gravity will behave consistently across environments that bear little resemblance to life near the ground. This situation can make gravity feel like a paradox. It behaves with remarkable precision in predictable circumstances, but becomes inconsistent the moment we examine systems large enough or unusual enough to test its boundaries. That duality makes it unique among forces. It raises the possibility that gravity may emerge from something more fundamental, or that it interacts with space in ways we don't yet grasp. Rather than being a simple attractive force, it might be a manifestation of deeper geometric or structural relationships. Or it might reflect something about the distribution of energy at a level we have not yet probed. Each proposal opens another path for exploration, yet none has settled comfortably enough to replace the original view. As we move toward the next ideas, the goal isn't to dismiss the established framework, but to understand why the quiet certainty around gravity may not match the reality revealed by observation. The force we thought we understood continues to surprise us, not by changing, but by refusing to fit into the neat categories we expected. That resistance invites us to keep looking, not for contradictions, but for explanations that can embrace both the simple pull beneath our feet and the complex motions unfolding across the universe. The journey continues one gentle step at a time, letting the details unfold without forcing them into a conclusion before they're ready. When you picture something falling, the motion feels so ordinary that it barely registers as something worth examining. You drop an apple from your hand and it follows a familiar downward path, landing exactly where you expect without much room for surprise. The motion feels tied to the ground below you, steady and predictable. But once you take that same idea and lift it out of the everyday world, once you bring it into the vastness beyond Earth, the picture becomes far less tidy. An apple falls because the ground draws it downward, yet when you shift your attention to the wide expanse of space, nothing stays still, nothing settles, nothing behaves as though it's caught by the same dependable tug. Instead of falling inward, the universe stretches outward. Instead of objects moving toward each other, whole regions drift apart. Something about that contrast makes the simple behavior of a falling apple seem almost misleading, as though it hides more than it reveals about gravity's true nature. If an apple drops toward the Earth, you probably don't stop to consider what the apple is actually doing in terms of space and motion. You're focused on the object itself, not on the invisible structure surrounding it. The apple isn't making a decision, nor is it reacting to any sensation. It simply follows the path that the environment guides it through. For most of history, people assumed this kind of motion required a straightforward pull, a force that acted at a distance and drew objects together. This explanation matched daily experience well enough. It felt natural, it worked for calculations near the ground, and it solved practical problems. But the simplicity was deceptive. As long as attention stayed close to home, the explanation appeared complete. The moment observations extended outward to space, the analogy between falling apples and celestial behaviour started to weaken. Once scientists gained the ability to measure the motion of planets with increasing precision, a new question arose. If everything experiences the same pull that brings an apple to the ground, why don't planets fall into the sun? Why don't moons drop toward their planets? The familiar answer is that they're moving sideways fast enough to keep missing the surface they orbit, creating a continuous state of falling without ever landing. It's a clever explanation, and useful for visualizing the motion. But if you step back from the analogy, something interesting appears. The sideways motion isn't a fundamental rule. Nothing demands that an object be given a sideways push to maintain a stable path around another. The explanation works, yet it doesn't reveal why space allows such motion, or why the surrounding environment shapes movement in that specific way. It treats gravity like a physical string pulling objects inward, while motion tries to escape outward. That's a simple picture, but not a complete one. A deeper interpretation emerged when scientists began examining how space itself behaves. The apple doesn't fall because of an invisible string. It falls because the ground creates conditions in which the apple has fewer possible paths that lead away from the Earth. Space near the Earth behaves in a way that guides objects inward. The apple simply follows the available path. This is where the contrast with space as a whole becomes striking. Near the Earth, paths bend inward. Across vast distances, paths bend outward. This isn't because different forces are operating in isolated pockets. It's because the structure of space isn't fixed. The environment changes from one scale to another. A small object falling near the ground experiences a curve in space that leads it inward. A distant galaxy moving through the cosmos experiences a shift in the opposite direction. The moment scientists realised that space could stretch, compress, or curve, the idea of a universal pull began to feel less certain. A falling apple feels like a direct response to a force, but the expansion of the universe feels like a kind of drifting that has nothing to do with the behaviour we see on Earth. If gravity simply pulled objects together, the universe should eventually slow its expansion or even reverse it. Instead, galaxies are moving apart faster than before. The farther something is, the faster it recedes. That behaviour has no counterpart in the simple experience of a falling apple. Apples don't accelerate upward when they get farther from the ground. They don't drift away more rapidly as they exit your hand. The everyday analogy collapses completely the moment you try to apply it to the larger scales. This mismatch raised an uncomfortable possibility. Maybe the rules we use to explain a falling apple work only in certain environments. Maybe the familiar pull exists only because space near the Earth behaves a certain way, and maybe the universe at large reveals the more general behaviour, one that doesn't align with the traditional notion of gravity at all. The apple's fall could be a local phenomenon, shaped by the Earth's influence, not a universal template for how motion works everywhere. The moment this thought enters the discussion, new questions unfold. If space can stretch, why does the stretching not influence the apple's motion in a noticeable way? If galaxies move apart, why doesn't the distance between your chair and the nearest wall expand along with them? The answer lies in how space behaves under different conditions. On small scales, the influence of nearby mass overwhelms the broader stretching. The Earth holds space in a particular configuration, anchoring the environment tightly enough that local expansion never overcomes the inward guidance. The apple follows this local shape of space rather than any larger trend. But once you leave that domain and examine regions far from significant concentrations of mass, the general behaviour takes over. Space stretches and objects drift with it. This duality makes gravity appear inconsistent, even though it might be entirely coherent within a broader framework we haven't fully grasped. The apple's fall isn't evidence of a universal downward pull. It's evidence of how space behaves near a large mass. The universe's expansion isn't evidence of an opposing force that pushes everything apart. It's evidence of how space behaves when mass is spread thinly across enormous distances. These aren't two separate rules. They might be different expressions of the same underlying behaviour. This interpretation shifts gravity from being a force to being an expression of motion through a changing environment. The apple falls because the environment it occupies is shaped in a way that leads it downward. Space expands because the environment across those vast regions isn't held tightly by concentrated mass. Instead of thinking in terms of pushing and pulling, the focus moves to the pathways objects naturally follow. And the moment this shift occurs, the relationship between apples falling and galaxies drifting no longer feels contradictory. They're simply responding to different surroundings. Yet this explanation leads to another puzzle. If space can shape motion so effectively, why does the universe allow the shape to be so different in different regions? Why does the Earth mould space in one direction while the cosmos moulds it in another? The answer may lie in the distribution of energy and mass. Where mass is dense, space curves in a way that guides objects inward. Where mass is sparse, space stretches as though it were relaxing outward. This balance creates an environment where local regions behave differently from the universe at large. Instead of thinking of gravity as a single force acting everywhere with uniform behaviour, we begin to see it as a pattern of responses to different conditions. But the more this idea is explored, the more difficult it becomes to rely on the traditional understanding. If the apple drops because space curves, what does it mean for the idea of a pull? If galaxies drift because space stretches, what does it mean for the idea of attraction? These questions reveal a tension that has grown over time. The familiar framework struggles to describe both the falling apple and the expanding universe without invoking additional elements that fill the gaps. Dark matter is introduced to hold galaxies together. Dark energy is introduced to drive expansion. These additions make calculations match observations, but they don't clarify why the apples fall and the universe's expansion feel like opposite behaviours. A clearer picture may emerge once gravity is viewed as something that doesn't follow a single universal rule. The apple's fall could be the local expression of how space responds to mass. The universe's expansion could be the large-scale expression of how space behaves when mass is dispersed. Both phenomena could be natural consequences of a system more subtle than a simple pull. If this interpretation is correct, then the reason apples fall while space refuses to sit still may not be a contradiction at all. It might be an invitation to stop thinking in terms of forces and start thinking in terms of environments. Local environments anchor motion. Cosmic environments release it. The familiar idea of gravity may be a convenient shortcut for describing one particular environment, not a universal description of all motion. This shift doesn't diminish the reliability of everyday predictions. Objects near the ground will continue to fall as they always have. Planes will fly using the same calculations. Satellites will orbit without deviation. But it does mean that the behaviour of the universe at large may demand a deeper interpretation, one that doesn't rely on comparing cosmic expansion to the fall of an apple. The analogy worked for centuries because the tools available at the time couldn't reveal the differences between local and cosmic behaviour. Now that those differences are unmistakable, the explanation must expand as well. Each new observation pushes the idea a little further. Every measurement of galaxy rotation, every analysis of cosmic expansion, every attempt to reconcile gravity with the behaviour of extremely small particles raises the same question. The apple's fall is real, but the universe refuses to behave as though falling is the default. That contrast doesn't break the system. It exposes the limits of the picture we've been using. Moving from one view to another doesn't require abandoning everything we know. It simply requires letting go of the assumption that gravity must behave the same way everywhere. That assumption held when observations were limited to the regions near Earth. It no longer holds when the entire cosmos enters the discussion. The next steps of this exploration continue from this realization, not by rejecting the familiar explanation, but by widening the frame enough to let both the falling apple and the drifting galaxies belong to the same coherent story without forcing one to mimic the other. Gravity has always given the impression of being straightforward, almost plain in the way it shows itself. You drop something and it moves downward. You stand still and the ground meets you with quiet certainty. Nothing about these motions suggests hidden complexity. Nothing hints that the space around you might be bending, shaping, or guiding the movement of everything you see. Yet once the idea emerges that gravity might not be a pull at all, but rather the result of something invisible shifting beneath our feet and around every object in existence, the familiar scenes of daily life take on a different tone. The floor beneath you isn't simply holding you. The space between you and the floor might be structured in a way that gently steers you downward. And once you begin imagining space as something that can curve, stretch, or settle into different shapes, gravity stops being simple. It becomes something far stranger, something both subtle and deeply influential, something hiding behind every motion you once thought you understood. When people first tried to picture gravity, imagining a pull made sense. It offered a clear explanation, something that didn't require thinking about anything you couldn't see. Yet the moment someone introduced the idea that space might not be rigid, that space itself could act like a pliable environment, capable of bending and shaping the motion of objects, the entire picture shifted. Suddenly gravity wasn't a force between masses, it was the effect of the environment guiding paths. The apple doesn't fall because the Earth tugs at it. It falls because the environment around the Earth is shaped in a way that leads the apple downward. This idea felt unusual at first because nothing in human experience suggests that space can bend. The air bends around objects, water bends when disturbed, but empty space appears silent and unchanging. Still, the more scientists studied motion across different scales, the more they realized that treating gravity as a direct pull created inconsistencies that treating it as a shape naturally resolved. Picture the surface of a flexible sheet. If you place a heavy object on that sheet, the material dips around it. If you then place a smaller object nearby, the smaller object will roll toward the heavier one, not because the heavy object pulls it, but because the environment around the heavy object has changed shape. The path toward the heavier object becomes the most natural path for the smaller one to follow. This image is only an analogy, though a helpful one. Space is not a sheet stretched across a frame. It's something deeper, something without edges, something that doesn't behave like any material you can hold. Yet the analogy captures one essential idea. When mass enters space, the environment around it changes, and that change influences motion. As soon as this perspective begins to settle, a quiet realization follows. Everything you ever attributed to a pull might instead be the result of a curve. Your body, sitting or lying comfortably, is resting in a region of space shaped by the mass of the Earth. Every movement you make follows a path shaped by that environment. Nothing in your daily experience reveals this directly, because everything familiar occurs within the same set of shapes. If the environment were to shift dramatically, you would notice immediately, but as long as the shape remains steady, you never question its influence. That invisibility is part of what makes gravity so elusive. Its effects are obvious, but its cause is silent. The first time scientists attempted to describe how mass shapes space, they realized quickly that the relationship was more complex than a simple dip. Space is not two-dimensional. There is no central spot where mass sits and creates a depression. Instead, mass influences the environment in every direction at once. The shape created is not a bowl, but an arrangement of paths. Each path represents the direction an object will follow naturally. When the mass is small, the environment changes only slightly. When the mass is enormous, the environment becomes profoundly altered. The Sun shapes space enough that planets can follow graceful paths around it. The Earth shapes space enough that objects fall inward. A black hole shapes space so dramatically that every nearby path leads inward without escape. What makes this idea even stranger is that space doesn't simply bend around mass. It curves in a dynamic way that responds to energy as well. Light, which has no mass, still follows the curves created by mass. Its path bends when it passes near a star or a massive cluster. This bending has been measured directly, with starlight shifting position when observed near massive structures. It's one of the clearest demonstrations that space is not passive. It reacts to the presence of mass and energy, forming channels that guide motion without ever revealing the shape itself to the senses. This invisible curving becomes even more intriguing once you consider that motion itself can shape space. When mass moves, the environment around it doesn't remain static. It changes subtly, adjusting with the movement, creating ripples that travel outward. These ripples are faint, extraordinarily faint, and only recently have scientists gained the tools sharp enough to detect them. They travel across the cosmos, carrying information about events so distant and powerful that they would otherwise leave no trace. The fact that we can detect these ripples proves that space behaves less like a rigid framework and more like a medium capable of transmitting disturbances. If gravity is the result of curved space, then the shapes we observe must reflect something deeper, about the way space responds to mass and motion. But even with this concept in hand, something didn't align fully. The curves predicted by theory didn't match the motions of galaxies. The shapes required to guide stars along their observed paths were far more pronounced than the visible mass could account for. The environment seemed more curved than it should have been. That discrepancy forced scientists to propose that either more mass existed than we could see, or something about the way space curved needed rethinking. The suggestion that additional mass existed became the dominant explanation, because it preserved the established framework. But the alternative remained in the background, a quiet reminder that perhaps gravity isn't just curvature, but a more complex interplay between mass, motion, and the structure of space itself. If space curves differently on large scales than on small ones, then the behaviour of galaxies might indicate a broader form of curvature, one that isn't accounted for by local observations. The theoretical curves we calculate near the Earth or the Sun might not extend cleanly into the cosmic environment. Instead, space may obey different patterns depending on scale, density, or energy distribution. This idea grows even more compelling once the expansion of the universe enters the picture. If space can curve inward near mass, it can also stretch outward where mass is sparse. These two behaviours may be two sides of the same phenomenon. On large scales, the stretching could overwhelm any inward curvature, guiding galaxies apart. On small scales, the inward curvature could dominate, guiding objects together. This balance creates a universe where both falling apples and drifting galaxies make sense without needing separate forces for each. Still, accepting that space curves isn't the same as understanding how it does so. Describing the shape requires complex mathematical tools, and even those tools might not reach deep enough to reveal the entire structure. Some researchers suspect that curvature itself might be only a visible effect of something more fundamental. Perhaps space is built from discrete elements rather than being smooth. Perhaps curvature emerges from the way these elements connect, interact, or shift. If that's the case, then gravity is not curvature itself, but the result of how the underlying pieces arrange themselves. Others propose that space has additional dimensions we cannot see. If true, curvature might occur not only in the familiar three dimensions, but also in directions hidden from ordinary perception. That could explain why gravity behaves so differently from the other forces, and why its influence spreads so effectively despite feeling so gentle. If mass shapes not only the visible environment but also hidden dimensions, the resulting motion we observe might appear weaker or stronger depending on how these unseen directions are involved. But when you return to the simple experience of an object falling, none of this complexity is apparent. The apple doesn't reveal anything about hidden dimensions or discrete structures. It simply follows a path determined by the environment around it. That simplicity is why gravity remained misunderstood for so long. The behaviour it displays near the ground offers no clues about the deeper reality. Only by examining environments vastly different from the ones we inhabit, regions near massive stars, clusters of galaxies, or cosmic voids, do the hidden features begin to emerge. This subtlety raises a striking thought. Perhaps gravity has never been a single thing. Perhaps the curves we attribute to mass are only one expression of a system that behaves differently under different conditions. In local environments, the curves are gentle and steady. In cosmic environments, they may stretch, shift, or intensify in unexpected ways. The universe may not be governed by one form of curvature, but by a landscape that changes depending on scale and density. If this is true, then our descriptions of gravity may have captured only the portion that applies to familiar environments. Everything we know about falling objects, planetary orbits, and satellite motion might represent just one part of a larger structure. The broader environment could include curves that behave differently, patterns that emerge only when distances grow enormous, and motions shaped not by attraction, but by the expansion or contraction of the underlying space. This interpretation doesn't contradict the usefulness of current gravitational models. It simply reframes them as accurate within specific boundaries. The deeper truth may be that gravity is not a simple act of curvature, nor a simple pull, but a dynamic shaping of the invisible environment, sometimes inward, sometimes outward, sometimes subtle, sometimes overwhelming. The curves we recognize are only the ones that appear frequently enough for us to notice. As we continue unfolding this story, the next questions build on this realization. If space curves, what shapes those curves beyond mass? If the invisible environment influences motion so effectively, what else might be guiding the behavior we see across the cosmos? Einstein's name has become so familiar that it's easy to forget how disruptive his ideas once were. When you hear that he bent the universe, the phrase can sound exaggerated, almost playful, as though he'd simply tugged on the corners of space like a blanket. Yet the shift he introduced was far more profound than a clever visual. Before his work, gravity was treated as a predictable pull, something acting at a distance without needing an explanation beyond the fact that it worked. The equations describing it had guided centuries of understanding, and although they showed cracks when stretched too far, they remained trusted. Einstein didn't set out to replace this system entirely. He was trying to understand motion, energy, and the limits of what earlier thinkers had proposed. But as he followed the questions where they naturally led, gravity transformed from a force to something deeper, something embedded in the structure of the universe itself. And once that idea took shape, nothing about the familiar pull of the ground felt quite as straightforward again. He began with a puzzle that sounds almost trivial. What would you feel if you were inside a falling elevator? Inside that elevator, you wouldn't feel the ground pulling at your feet. You wouldn't feel heavy. You wouldn't feel like you were falling at all. Everything around you would drift, weightless, as though gravity had vanished. But step outside that elevator, or imagine watching it from solid ground, and the situation looks entirely different. Gravity hasn't disappeared. The elevator is rushing downward under its influence. Einstein realized that the person inside the elevator and the person observing from outside were living in two completely different versions of the same situation. He saw that if acceleration and gravity could imitate each other so perfectly, they might share a deeper connection. This realization became the seed of a much broader insight. Gravity might not be a force at all, but a feature of the environment shaping how objects move. That idea sounds odd because everyday life gives no hint that the ground beneath you is shaping space. When you walk across a room, you feel no distortion, no curvature, no invisible tilting of paths. Your senses insist that space is flat, uniform, unmoving. Yet Einstein's calculations showed that space couldn't remain flat if the familiar effects of gravity were real. Something had to guide motion. Something had to create the paths that falling objects followed. The old notion that objects pulled each other like magnets acting through empty air didn't explain how the interaction travelled, or why it behaved with such consistent geometry. Instead of imagining an invisible pull, Einstein imagined that the presence of mass changed the structure of the environment. Objects then followed the available path through that environment. Nothing was pulling them. They were simply moving naturally within the shape surrounding them. This perspective made the old force-based idea unnecessary, though not immediately replaceable. It required a new framework, one that linked motion, mass, and space into a single coherent system. Einstein spent years building the mathematics that could describe these relationships. The equations that eventually emerged didn't look like earlier laws. They didn't describe force, acceleration, or attraction. They described curvature, structure, and the way mass influences the geometry of the environment. Once the equations were complete, their implications were startling. They predicted that light would bend around massive objects. They predicted that clocks would tick at different rates depending on where they were placed. They predicted that even the flow of time depended on the shape of the environment. None of these predictions felt intuitive, but they made sense within the new system. If mass curves space, then light should follow those curves. If mass affects the environment, and time is part of that environment, then time must shift as well. Gravity was no longer a separate influence. It had merged into the fabric of the universe. When Einstein said that mass tells space how to curve and space tells matter how to move, he wasn't making a poetic statement. He was describing the precise relationship expressed by his equations. The universe wasn't a stage where events played out. It was an active participant, shaping motion through its structure. One of the first tests of this new idea came from observing starlight passing near the sun. According to Einstein's calculations, the starlight should bend slightly as it travelled through the curved environment surrounding the sun. During a solar eclipse, astronomers measured this bend directly, confirming the prediction. It was a moment that changed the course of scientific thought. A theory once considered uncomfortably abstract had revealed something hidden in plain sight. For the first time, the invisible shaping of the universe had left a measurable mark on the sky. This success didn't mean the new theory was immediately accepted on all fronts. Many scientists struggled with the idea that space could bend or that time could run differently depending on circumstances. But the predictions continued to match observations, and gradually the old picture faded. The universe wasn't static, it wasn't rigid, it wasn't a passive container, it was dynamic, flexible and responsive. Gravity became a side effect of this flexibility. When the Earth curves the environment around it, objects near the surface follow the available paths in that environment. You feel yourself being held down, but what you're really experiencing is the geometry of the world you inhabit. As Einstein explored this system further, he realized that it could describe not only local curvature, but also the behavior of the universe as a whole. His equations suggested that the environment wasn't static. It could expand or contract depending on the distribution of mass and energy. At the time, most scientists assumed the universe was fixed and unchanging, so the idea of expansion felt unnecessary. Einstein himself introduced an additional term to keep the universe stable, because the alternative seemed unlikely. But once observations revealed that galaxies were moving away from each other, his original equations without the stabilizing term turned out to be correct. The universe really was expanding. This insight tied gravity and cosmic expansion together in a way that changed the question scientists asked. Gravity wasn't simply shaping motion on Earth or within our solar system. It was shaping the environment of the entire universe. When matter gathers in one region, the environment curves inward. When space stretches across large distances, the environment shifts outward. These aren't competing forces, they're different expressions of the same system, one that responds to mass and energy at every scale. Yet even with the elegance of this explanation, new puzzles emerged. Einstein's equations could describe the curvature caused by matter, but they didn't explain why galaxy clusters held together more tightly than expected. They didn't explain why galaxies spun faster than their visible mass allowed. They didn't explain why the universe's expansion was accelerating. Instead of challenging the idea that curvature came from mass and energy, scientists introduced concepts like dark matter and dark energy to fill the gaps. These additions worked mathematically, but they added layers of mystery. Einstein's framework could bend the universe, but it couldn't reveal everything shaping its motion. The deeper scientists looked into the curvature of space, the more they realized that Einstein's theory, while powerful, might not be the final explanation. It succeeded in describing how curvature works, but it didn't explain what space was made of or why curvature behaved differently in different environments. The theory blended space and time into a unified structure, yet it struggled when brought into contact with the quantum world. Quantum mechanics treats the universe in discrete pieces, with probabilities and fluctuations. Einstein's theory treats the universe as smooth and continuous. Reconciling these perspectives has become one of the greatest ongoing challenges in physics. Despite these tensions, the idea of bending space remains foundational. It reshaped everything from our understanding of black holes to our interpretation of cosmic expansion. It redefined gravity from something mysterious and long distance to something structural and immediate. When you stand still and feel the ground beneath you, you're experiencing the shape of your environment. When a satellite orbits the Earth, it's following the natural path through curved space. When light bends near a massive object, it's not being pulled. It's travelling along the shape created by mass. Einstein's insight didn't eliminate the mysteries of gravity. In many ways, it made them deeper. Instead of wondering how objects pull on each other, we now wonder what space is and why it curves. Instead of searching for a mechanism of attraction, we search for a framework that unites curvature with quantum behaviour. Instead of asking why objects fall, we ask why the environment they move through takes the shape that it does. Yet the shift Einstein introduced remains one of the most profound in the history of science. He showed that gravity doesn't act from a distance. It arises from the relationship between mass and the environment. He showed that paths through space aren't straight lines unless nothing influences them. He showed that time isn't a universal constant ticking away. identically everywhere. Time itself is shaped by the environment, running slightly faster or slower depending on how curved the surroundings are. These ideas feel strange because they don't appear in everyday life. The curvature near Earth is too subtle to feel. The stretching of space between galaxies is too slow to sense. The bending of light is too slight to notice without precise instruments. But the subtlety doesn't reduce the significance. It simply reminds us that the universe often hides its deepest truths behind motions that appear ordinary. Einstein's contribution remains a turning point. He replaced the familiar pull with landscape. He replaced distance-based force with structure. And in doing so, he offered a picture of the universe that accommodates both the certainty of a falling apple and the drifting of galaxies. The questions that follow build from this foundation, examining where this model succeeds, where it struggles, and what new ideas might push our understanding beyond even the bending of the universe itself. When you look at gravity through the lens of everyday experience, it feels orderly. Objects fall, planets move in steady paths, structures stay grounded. Nothing in that familiar rhythm suggests that gravity might behave unpredictably or hide gaps in our understanding. Yet once scientists pushed beyond the boundaries of what could be seen with the naked eye or tested in simple experiments, they encountered situations that didn't line up with the rules that had seemed so dependable. These weren't minor irregularities. They were consistent patterns, repeating across distant systems, implying that something important was missing from the framework that had worked so well for so long. The mysteries began as quiet discrepancies, but the more carefully they were measured, the more clearly they revealed that the old rules could not explain everything. One of the earliest signs that something was amiss came from astronomy. Observers tracking the motion of planets in our own solar system noticed small deviations from the predicted paths. Most of these differences could be explained once new planets were discovered or once tools became more precise. But Mercury, the planet closest to the Sun, refused to cooperate perfectly. Its orbit shifted slightly in a way that couldn't be aligned with existing equations. The discrepancy wasn't enormous, but it persisted. When Einstein introduced the idea that gravity resulted from the curvature of space rather than a straightforward pull, the mystery of Mercury's orbit fell neatly into place. The new framework accounted for the irregularity, showing that the old rules had reached their limit. That moment should have been a warning that the rules might break down further under different conditions, but for a time, success encouraged confidence. As telescopes grew stronger and techniques improved, the next major mystery arrived from the scale of galaxies. When researchers measured how fast stars moved around the centers of their galaxies, the speeds didn't match the predictions. According to the rules, stars farther from the center should move more slowly, just as planets farther from the Sun move more slowly than those close in. Yet that wasn't what the data showed. Stars at the edges of galaxies moved far faster than expected. The rules said they shouldn't be able to hold together at those speeds, yet they did. Something was providing additional influence, strengthening the gravitational hold. The simplest explanation became that there must be more mass present than could be seen. If galaxies contained much more material than was visible through telescopes, the unseen mass could provide the extra gravitational influence needed to keep stars in place. That idea led to the proposal of dark matter. It wasn't meant to be mysterious. It was simply a placeholder for mass that wasn't visible. But as more galaxies were measured, the pattern became universal. Everywhere scientists looked, galaxies behaved as though they contained far more mass than their visible components indicated. Dark matter became a necessary addition to the rules. Yet even with this explanation, the situation wasn't comfortable. The concept worked mathematically, but there was no direct evidence for the substance itself. Experiments designed to detect dark matter continued with increasing sensitivity, but none produced confirmation. The more time passed without detection, the more the mystery grew. It wasn't a small adjustment to the rules. It implied that most of the mass in the universe, far more than all visible stars and planets combined, was made of something unknown. The rules fit the data only by adding an enormous invisible ingredient, and the theory depended on this ingredient to remain valid. Another mystery emerged when scientists examined clusters of galaxies. A single galaxy refusing to follow predictions could be treated as an isolated case, but clusters held even more surprises. These vast collections of galaxies moved and interacted, as though something more substantial bound them together. According to the rules, they should not remain intact. The visible mass was far too little to produce the gravitational stability observed. Once again, the idea of dark matter offered a neat solution. If clusters contained large amounts of unseen material, their behavior made sense, but the amount required was even greater than in individual galaxies. The rules fit only by assuming that an overwhelming majority of the mass was invisible. This pattern continued, with dark matter becoming essential for explaining not just galaxy rotation and cluster stability, but also the behavior of the universe on even larger scales. Each new set of measurements relied on dark matter to reconcile the equations with observation. But as the need for it grew, so did the discomfort. It wasn't one mysterious ingredient, it was a dominant component of the universe, and yet, despite all efforts, it remained undetected. The next major mystery came from something even more surprising than missing mass. While studying distant galaxies, astronomers expected to see that the expansion of the universe was slowing. Gravity, even with dark matter included, should cause the expansion to decelerate over time. But the data showed the opposite. Instead of slowing, the expansion was speeding up. Distant galaxies were drifting away faster and faster. This behavior didn't fit the rules. The expansion had to be accelerating, but no known force could produce that effect. To explain this accelerating expansion, scientists introduced another new ingredient, dark energy. The term didn't describe a known substance, it described the effect needed to match observation. Something had to push galaxies apart. Something had to cause space to stretch more rapidly. In earlier eras, proposing a completely unknown form of energy might have seemed extravagant, but the equations offered no alternative. The rules required a new component, and dark energy became that component. Yet the introduction of dark energy added another layer of mystery. If the universe was filled with a substance or effect powerful enough to accelerate expansion, why didn't it influence everyday environments? Why didn't it alter the behavior of local systems? The explanation was that dark energy acted only on very large scales, becoming noticeable only when vast distances were involved. But that distinction created a divide between small-scale and large-scale behavior. The rules worked one way near stars and planets, another way across cosmic distances. That division raised the possibility that perhaps the rules themselves were incomplete. Perhaps gravity behaved differently depending on scale, rather than being a single universal interaction. Another mystery appeared as physicists attempted to reconcile the rules of gravity with the rules of quantum mechanics. On the scale of the very small, particles behave according to a framework built on probabilities and discrete interactions. Gravity, described by Einstein's theory, behaves according to continuous curvature. The two frameworks work well independently, but collapse when brought together. Attempts to merge them produce contradictions, infinities, or undefined results. The rules for gravity refuse to blend with the rules for particles. This failure suggests that gravity might arise from something deeper, something not captured by either theory. One possibility is that space-time itself might not be smooth. It might have a granular or layered structure at extremely small scales. If so, the curvature described by Einstein might be an approximation that works well in everyday environments, but breaks down when examined closely. This could explain why gravity doesn't integrate well with quantum rules. The frameworks might be describing different layers of reality, but without the ability to measure space-time at such small scales, this idea remains speculative. Another mystery involves the behavior of gravity in regions of extreme density, such as the centers of black holes. According to the rules, curvature becomes infinite in these locations, but infinity is a sign of theoretical failure. It indicates that the equations are being pushed beyond their domain. Black holes highlight the sharp boundary where the rules collapse. They show that while the current understanding of gravity works in many situations, it cannot describe all environments. Even the idea of mass-producing curvature raises questions. What counts as mass? What role does Ng play? How does pressure contribute? The equations link mass, energy, and curvature, but the relationships become complex in dynamic systems. If an object changes shape or density rapidly, how quickly does the surrounding environment adjust? How does the curvature propagate? These questions matter when examining phenomena such as neutron stars or merging black holes. The rules describe these events, but only up to a point. Observation suggests there are layers to the behavior that remain unexplained. The mysteries also extend to the larger structures in the universe. Maps of cosmic background radiation reveal small variations in temperature and density. These variations grew into the structure we see today. But the rules alone can't explain how regions far apart developed identical properties without exchanging information faster than light could travel. This issue, known as the horizon problem, led to the proposal of cosmic inflation, a period of rapid expansion in the early universe. Inflation solves the problem mathematically, but its cause remains unknown. Once again, the rules work only with an added ingredient. These patterns reveal something consistent. The rules function well within certain limits, but outside those limits, they require additions, modifications, or exceptions. The more scientists investigate regions of high density, large distance, or early cosmic time, the more the mysteries accumulate. The framework must twist and stretch to accommodate new observations. Instead of a simple, unified rule, gravity begins to look like a set of approximations that fit specific environments. Each unexplained phenomenon pushes the idea further away from being a complete description and closer to being a visible section of a larger, more complex structure. This doesn't diminish the achievements of existing theories. Satellites operate correctly. Spacecraft navigate reliably. Observations of local systems match predictions. But these successes do not eliminate the deeper mysteries. They highlight how well the rules work in their domain while revealing the edges where they break down. Galaxies give the impression of calm when seen from far away. Their spiraling arms look soft, almost delicate, as if they're drifting through the universe with the same gentle patience you feel when watching the sweep of a slow tide. But beneath that peaceful appearance lies a problem that has puzzled scientists for decades. When researchers began measuring how fast galaxies actually spin, they expected the motions to follow the rules that had worked so well for planets orbiting the Sun. Instead, they found something that didn't fit the familiar pattern at all. Stars at the edges of galaxies were racing around far faster than they should have been, and according to everything the rules of gravity predicted, the galaxies should have torn themselves apart. The speed simply didn't match the amount of visible material inside those galaxies. Something wasn't adding up, and that mismatch revealed one of the largest mysteries in modern science. When you think about the motion of planets in our solar system, the pattern is straightforward. The planets close to the Sun move quickly. Those farther away move more slowly. The Sun's gravitational influence weakens with distance. This decline is predictable, smooth, and well understood. If a distant planet suddenly moved as quickly as an inner one, it would escape its orbit entirely. So the pattern holds. Distance determines speed. That framework seems natural enough. For a long time, scientists assumed galaxies would follow the same rule. After all, a galaxy is just a much larger version of a solar system, stars instead of planets, a central bulge instead of a sun. The expectation made sense, it just turned out to be wrong. When astronomers measured the rotation speeds of stars at different distances from the centre of a galaxy, they discovered that the pattern did not mirror the solar system at all. Instead of slowing down with distance, the stars maintained nearly constant speeds. Some even moved slightly faster. According to conventional gravity, which depends on the amount of mass inside a given orbit, the outer stars should have moved far more slowly, barely hanging on. The fact that they didn't slow meant that either something was providing extra gravitational influence or the understanding of gravity itself needed revision. To make sense of the situation, scientists calculated how much mass would be needed to hold those fast-moving stars in place. The answer was unsettling. The visible stars, gas and dust in the galaxy accounted for only a small fraction of the required mass. Most of the influence had to come from something unseen, substantial enough to bind the galaxy, subtle enough to escape detection. This imbalance led to the proposal of dark matter, but the mystery extended beyond that name. The concept itself came with questions. What was this unseen mass? Why didn't it interact with light? Why didn't it form structures like stars and planets? It was a convenient solution, but it didn't satisfy the deeper curiosity about why galaxies behave so strangely in the first place. Once the rotation curves of galaxies became widely studied, the same pattern appeared everywhere. No matter where scientists looked, the speeds refused to match predictions. Spiral galaxies, elliptical galaxies, dwarf galaxies, across the board, the stars orbited too quickly for their visible mass. The phenomenon wasn't an oddity, it was universal. That universality made the mystery impossible to dismiss. The rules that govern solar systems simply didn't apply to galaxies in the same way. The cosmic scale introduced behaviour that the older framework had never anticipated. This inconsistency raised a quiet but persistent question. Were the rules truly universal, or had they been stretched beyond their intended range? Perhaps gravity worked differently on large scales. Perhaps the curvature of the environment behaved differently when mass was spread across great distances. Perhaps something happened in the vast emptiness between stars that didn't occur in smaller systems. The idea that gravity changed with scale wasn't welcome at first, but it didn't go away because the data refused to cooperate with simpler explanations. Over time, researchers began to map these rotation curves with increasingly refined techniques. They used radio waves to track the movement of hydrogen gas in galaxies, allowing them to measure motion far beyond the reach of visible light. The same pattern persisted. The gas at the edges moved too fast. Even galaxies that were dim and nearly invisible showed the same unexpected rotation. The rules that described planetary motion were no longer enough. Something more expansive was shaping these systems. Some scientists turned to the idea that perhaps galaxies contained matter that didn't emit light. Mass that was invisible but still influenced gravity. This approach became the mainstream explanation because it preserved the core understanding of gravity while adding a new ingredient. It framed the mystery as a problem of missing mass rather than a problem with the rules. But the missing mass wasn't just a small adjustment. In many galaxies, the invisible component outweighed the visible matter by a factor of 10 or more. That scale raised suspicion. If most of the mass in the universe was invisible, how had it escaped detection for so long? Why didn't it form structures we could observe? Why didn't it interact in the usual ways? One reason the missing mass idea persisted was that it made the equations work. When dark matter was included, rotation curves matched predictions. But relying on invisible mass didn't resolve the deeper question of why galaxies behaved differently in the first place. The success of the idea masked the possibility that gravity itself might behave differently. Some researchers began exploring alternatives, not because dark matter had failed, but because the mystery felt broader than a simple imbalance in mass. One of these alternatives suggested that gravity weakened less at large distances than previously assumed. In this interpretation, the force didn't fall off as steeply, allowing galaxies to spin rapidly without flying apart. Another approach considered the structure of space itself. If space behaved differently on large scales, Perhaps the environment shaped galaxy motion independently of the mass distribution. The curvature could act not just around individual stars but across entire regions, guiding motion in ways not accounted for by the smaller scale equations. These ideas didn't replace the prevailing explanation, but they introduced new ways to think about the problem. Instead of assuming galaxies contained vast amounts of invisible material, the alternative perspective considered whether the environment might shape galaxy motion differently than expected. If gravity was not a uniform rule but something that responded to scale, density, and structure, the unusual rotation curves might be a natural consequence of that deeper behaviour. Yet the more researchers explored the idea of dark matter, the more layers the mystery gained. If dark matter shaped galaxy rotation, it should also influence the formation of galaxies. It should clump in specific ways. It should leave traces in cosmic background radiation. And indeed, the patterns observed in deep sky maps seem to support these predictions. But the support was indirect. It depended on assuming dark matter existed rather than detecting it. Experiments continued to search for direct signs of the material, but nothing confirmed its presence. This absence raised the possibility that the rotation problem might be pointing not toward a hidden material, but toward a missing piece in the understanding of gravity. As computers grew more powerful, simulations became a central tool in exploring galaxy behavior. Scientists created digital galaxies containing both visible matter and large volumes of unseen mass. These simulations produced galaxies that looked remarkably like the ones observed. The spiral arms formed correctly, the motions aligned, the structures matched. The success of these models strengthened the dark matter explanation. Yet simulations depended heavily on assumptions built into the equations. They matched the observed universe by construction. The results were impressive but not definitive. Meanwhile, alternative theories continued to examine whether the rules themselves required adjustment. Some proposed that gravity might transition between behaviors depending on acceleration. Others suggested that inertia might behave differently on cosmic scales. Some explored the idea that mass might interact with space in ways not accounted for in existing theories. The details varied widely, but they shared a common foundation: the suspicion that galaxy rotation curves were a message, not a mistake. They pointed to a layer of gravitational behaviour that the current framework had not captured. One curious pattern strengthened this suspicion. When researchers compared the visible mass of a galaxy to its rotation curve, they found a consistent relationship. The amount of visible material aligned with the unexpected speeds in a way that suggested a deeper link. If dark matter dominated galaxies, the rotation curves should vary in unpredictable ways depending on how dark matter was distributed. But the relationship remained consistent across galaxies of different sizes, shapes, and environments. This uniformity hinted that gravity might be responding to the visible material directly, rather than to an unseen component. Another strange feature emerged: galaxies that were extremely small, those with very little visible mass, sometimes rotated more slowly than dark matter models predicted. Some dwarfs behaved exactly opposite to expectations, showing less gravitational influence than the dark matter explanation required. These outliers complicated the idea that dark matter alone could explain galaxy motion. The data suggested that something more nuanced was at work. The mystery deepened further when researchers examined galaxies in different environments. Some galaxies embedded in dense clusters behaved differently from isolated ones. The differences couldn't be explained by visible mass alone or by simple adjustments to the amount of dark matter. Instead, the behaviour seemed to reflect the environment surrounding the galaxy. Gravity appeared to depend not only on the internal mass but also on broader conditions. This environmental dependence didn't contradict dark matter, but it suggested that the motion reflected more than just mass distribution. One interpretation of these patterns proposed that the curvature of space might have different forms depending on scale. Galaxies might inhabit environments where the curvature follows different rules from those governing small systems. If the structure of the universe influenced the shape of space differently across regions, then motion would naturally diverge from the small-scale predictions. Under this view, galaxies spinning too fast might not be accelerating beyond the rules, but simply responding to a shape that the current framework could not describe. Another idea considered whether inertia itself might behave differently on galactic scales. Instead of mass resisting motion, in the same way everywhere, perhaps the resistance depended on the environment. This would allow galaxies to move in ways that seemed inconsistent with the simpler framework, without invoking invisible mass. These ideas were controversial, not because they lacked support, but because they required rethinking assumptions that had become foundational. Despite the tension, the mystery of galaxy rotation remains one of the most important clues in modern science. It reveals that either the universe contains vast amounts of unseen material, or that gravity is incomplete. Both possibilities carry implications far beyond galaxy motion. If dark matter exists, it must play a central role in shaping the universe, guiding structure formation, influencing expansion, and interacting with the environment in subtle ways. If gravity is incomplete, the path forward requires rethinking not only galaxy motion, but also the framework that connects space, time, and mass. The galaxies that spin too fast for their own good are not mistakes. They are markers, pointing toward the next layer of understanding. Their unexpected motion is not a disruption but an invitation to explore the deeper structure of the universe, one that continues revealing complexities we're only beginning to unravel. Dark matter has become one of the most familiar scientific mysteries of our time, but its name can be misleading. It sounds like a substance, something tangible yet hidden, something lurking in the universe waiting to be uncovered by sharper instruments or more patient experiments. But the truth behind the term is far less concrete. Dark matter isn't a discovered thing. It's an idea, a placeholder introduced to explain motions that the existing rules couldn't account for. When galaxies spun too quickly, and galaxy clusters held together too strongly, dark matter entered the story not because anyone had detected it, but because the equations needed it to balance. It became a ghost in the arithmetic, the silent partner in calculations that otherwise would fall apart. Over time, this ghost transformed from a temporary suspicion into a central component of the universe, shaping the structure of everything at a scale that seemed unimaginable when the idea first appeared. The concept emerged slowly, beginning with subtle inconsistencies in the motions of galaxies. Astronomers observed stars circling rapidly at the edges of spiral galaxies, moving much faster than the visible mass could support. According to the rules that had guided celestial mechanics for centuries, those stars should have drifted away or never settled into their orbits to begin with. But they stayed in place. Something had to be holding them. When researchers tallied the mass of the stars, gas and dust, the numbers fell dramatically short. Instead of trying to revise the rules of gravity, many reached for an alternative. Assume more mass existed than was visible. The missing ingredient became the logical correction, the way to reconcile theory with observation without discarding the familiar framework. This assumed mass had to behave differently from ordinary matter. It couldn't emit light, reflect it, or absorb it. It couldn't form stars or planets. It couldn't participate in chemical reactions. It had to be everywhere and nowhere at once, interacting through gravity but not through light. These requirements made the idea unusual, but they also made it convenient. If dark matter existed, then the galaxy's unexpected motions weren't violations of the rules. They were reminders that the universe contained more than met the eye. The more astronomers applied the concept, the more indispensable it became. Rotation curves matched predictions once enough dark matter was added. Galaxy clusters remained stable. The formation of early structures in the universe followed patterns consistent with simulations that included large amounts of hidden mass. The ghost carried the weight that visible matter could not, and in doing so it strengthened the idea that the rules themselves were sound. As the idea grew, so did its influence. dark matter became part of the standard model of cosmology, shaping discussions of how the universe formed and evolved. Maps of cosmic background radiation showed tiny variations in temperature and density, patterns that aligned with dark matter influencing structure from the earliest moments. Simulations of galaxy formation, massive digital experiments run on supercomputers, produced realistic results only when dark matter played a central role. These successes made the concept feel increasingly real, even though it remained unobserved directly. It was as though the universe behaved exactly as if dark matter existed, yet refused to reveal the substance itself. Researchers began searching for particles that could play the role dark matter required. The candidates needed to be massive enough to exert gravitational influence, but subtle enough to avoid all other interactions. They couldn't interact with light. They couldn't collide frequently with ordinary particles. They had to be stable across cosmic time. These constraints narrowed the possibilities, leading to ideas about weakly interacting particles, massive neutral particles, and other hypothetical entities. Experiments were designed to detect the faintest of interactions between these ghost-like particles and ordinary matter. Deep underground laboratories were built to shield detectors from background noise. Colliders were used to create high-energy conditions where new particles might appear. Yet despite the enormous effort, the detectors remained silent. The silence didn't weaken the belief in dark matter. Instead, the lack of detection encouraged more creative hypotheses. Perhaps the particles were lighter than expected. Perhaps they interacted even less than predicted. Perhaps they existed in forms that detectors weren't designed to capture. Each null result didn't eliminate the idea. It expanded it. The more places dark matter wasn't found, the more flexible the concept became. This flexibility made it difficult to challenge. An idea that can stretch to fit any outcome becomes harder to test, harder to confirm, and harder to reject. The ongoing absence of direct evidence raised a quiet but persistent concern among some scientists. Were they searching for something that truly existed? Or had the ghost become too comfortable in the equations? It was a subtle question, not an accusation. The success of dark matter in explaining observations couldn't be ignored, but neither could the fact that after decades of searching, nothing tangible had emerged. This situation didn't necessarily mean the idea was wrong. Many important scientific concepts took centuries to confirm, yet it did raise the possibility that the universe might be hinting at something deeper, something not captured by the assumption of missing mass. One alternative perspective suggested that the behavior attributed to dark matter might reflect a change in the way gravity works at large scales. Instead of adding mass to compensate for unexpected motion, this approach considered whether the rules of gravity needed adjustment. For example, if gravitational influence weakened less with distance than expected, galaxies could spin fast without needing additional mass. If inertia behaved differently in regions with extremely low acceleration, the rotation curves might emerge naturally. These ideas weren't mainstream, not because they lacked evidence, but because they challenged a framework that had been remarkably successful in explaining numerous phenomena. Still, they persisted. Some researchers found that modifying the rules of gravity produced predictions that aligned with observations across a wide range of systems. The relationship between visible mass and rotation speed, which should have been unpredictable if dark matter dominated, followed a consistent pattern instead. This consistency suggested that the visible matter might play a more direct role in shaping motion than previously thought. It didn't eliminate the possibility of dark matter, but it showed that alternative explanations could also capture the mysterious behavior of galaxies. Despite these alternatives, dark matter remained the favoured explanation because it fit seamlessly into the broader model of cosmic evolution. Without dark matter, the large-scale structure of the universe was difficult to explain. The early universe wouldn't have formed galaxies quickly enough. Clusters wouldn't have grown as they did. The cosmic web, a vast network of filaments stretching across billions of light-years, would look very different. Simulations without dark matter failed to reproduce these patterns. the ghost was too helpful to discard. Yet relying on dark matter introduced complications that had to be managed carefully. If most of the mass in the universe was invisible, then understanding how that mass behaved became essential. But dark matter didn't behave like ordinary matter. It didn't clump tightly. It didn't heat up or cool down. It didn't radiate energy. It influenced motion but remained unresponsive to anything except gravity. This one-dimensional nature made it difficult to study. The ghost acted through gravity alone, leaving a narrow trail of clues. Each clue pointed in the same direction, toward a vast, invisible presence shaping the universe, yet none provided a definitive answer about what that presence was. The more this ghost shaped the universe in theory, the stranger it became. If dark matter filled the cosmos, why didn't it accumulate into dense objects like stars or planets? Why didn't it collapse into black holes? Why didn't it create structures larger than galaxies? The rules governing dark matter had to be written in a way that explained not only what it did, but what it didn't do. It had to be stable, yet dynamic, influential, yet aloof, abundant, yet elusive. The more clearly its behaviour was defined, the more peculiar it looked. Some researchers began to wonder if dark matter might not be a substance at all. Perhaps it was an effect arising from a deeper principle, something that appeared as missing mass only because the framework for interpreting motion was incomplete. In this interpretation, dark matter might be a mathematical artifact, a sign that gravity behaves differently than assumed. The ghost might not be a real entity, but a shadow cast by an incomplete theory. Its presence in the equations could be a clue that something more fundamental was waiting to be uncovered. This idea grew stronger as new observations revealed inconsistencies in the dark matter framework. Certain galaxies, especially dwarfs, didn't follow the expected patterns. Some showed less gravitational influence than dark matter should have provided. Others showed unexpected distributions of motion. These anomalies didn't break the dark matter model, but they highlighted areas where it struggled. If dark matter was truly the dominant component of the universe, its influence should be more uniform. The variation suggested that something else might be involved. Meanwhile, new detections of gravitational waves, the ripples in space produced by massive collisions, offered another perspective. These waves provided a new way to study the curvature of space itself. If dark matter affected curvature differently than normal mass, the waves might reveal subtle signatures. So far, the observations haven't shown evidence of such distinctions, leaving the ghost unconfirmed once again. The waves traced paths predicted by existing theory, but they didn't illuminate the nature of the effect shaping them. Another layer of the mystery came from the distribution of dark matter in galaxies. Observations reveal that dark matter didn't form dense cores, but rather diffused halos stretching far beyond the visible edges. These halos influenced the motion of stars and gas, but their shape didn't match the patterns expected if they were made of particles interacting under gravity alone. The halos seemed smoother than predicted, as though something softened their structure. This raised questions about how the hypothetical dark matter interacted with itself, if at all. None of these puzzles eliminated the ghost. They simply deepened its presence in the discussion. The more difficult dark matter became to detect, the more researchers refined their tools. New observatories probed deeper into space. New detectors searched for rare collisions. New simulations explored countless variations. Yet the ghost continued to elude direct contact. It remained a concept that explained everything about certain motions and nothing about its own nature. The enduring appeal of dark matter comes from its ability to make the universe coherent. It ties together phenomena that otherwise would appear disconnected. Without it, galaxies don't hold together. Clusters drift apart. The cosmic web dissolves. The early universe wouldn't evolve into the structure we see today. The ghost is the unifying thread, but its power to unify comes at the cost of complexity. It forces scientists to imagine a universe filled mostly with something unobserved, something that can neither be felt nor interacted with directly, something that shapes everything without revealing what it is. As the story of gravity unfolds, dark matter represents a crossroads. One path leads deeper into the search for the invisible mass that shapes the universe. The other path leads toward a reconsideration of the rules themselves. Neither option is simple, and neither is complete. What's certain is that galaxy motion, cluster stability, and cosmic structure all point to something beyond the familiar. The discovery of dark energy began not with a dramatic breakthrough but with a quiet surprise. One so unexpected that the scientists who found it initially thought they had made a mistake. Up until that moment, the idea that the universe might be slowing down had felt so natural that few questioned it. If mass attracts mass, then everything drifting outward from the earliest expansion should gradually lose momentum. The universe should be expanding, yes, but decelerating in the process. That expectation matched the rules that had guided cosmology for decades. Yet when astronomers examined distant galaxies and measured how their light had stretched over time, they confronted a pattern that overturned the comfortable assumption. The expansion wasn't slowing at all, it was speeding up. The universe was accelerating, as though something hidden was pushing everything apart. This discovery changed not just the numbers in the equations, but the entire landscape of cosmic understanding. To make sense of the acceleration, scientists needed to introduce something entirely new, an influence that acted across the universe, didn't come from mass, and pushed outward instead of pulling inward. That influence became known as dark energy. The name didn't describe a known substance. It simply labelled the effect needed to match the data. It was a placeholder, a way to acknowledge that something was happening without pretending to know what it was. The more researchers studied the acceleration, the clearer the message became. The universe wasn't just expanding, it was being driven apart by an influence utterly unlike anything familiar. At first glance, the idea that empty space might contain energy seems counterintuitive. When you imagine emptiness, you picture nothing at all. But physics doesn't treat emptiness as a simple void. Even a perfect vacuum contains fluctuations, tiny eruptions of energy that emerge and vanish too quickly to be observed directly. Some theories propose that these fluctuations might accumulate into a subtle outward pressure. If space itself contains energy, then as the universe grows, that energy accumulates. More space means more energy, and more energy means stronger expansion. This idea helps scientists imagine how cosmic acceleration might occur without invoking forces acting at specific points. Instead of something pushing from the outside, the expansion could arise from the environment itself. But the moment this idea entered the discussion, new questions emerged. If empty space contains energy, why doesn't it affect the motion of objects near the ground? Why doesn't it influence the pull you feel when you drop something? The explanation lies in scale. On small scales, like the distance between your feet and the floor, the influence of the Earth overwhelms any contribution from the energy in empty space. But on large scales, where mass becomes sparse and distances stretch across billions of light years, the outward influence of dark energy begins to dominate. This distinction creates a universe where local environments behave in one way and cosmic environments in another. Near mass, inward curvature controls. Across vast distances, outward stretching wins. This division between local and cosmic behaviour is one of the most unsettling features of dark energy. It means that gravity is not simply a universal attraction acting consistently everywhere. Gravity competes with dark energy, and the outcome depends on the scale. In regions with dense mass, gravity prevails. In regions where matter thins out, dark energy pushes space outward. The result is a universe where the rules vary depending on context, a possibility that many scientists initially resisted, but which the data forced them to accept. The puzzle deepens further when you consider how much of the universe dark energy comprises. If the calculations were correct, dark energy should account for nearly 70% of the total energy in the universe. Ordinary matter, the kind that forms stars, planets, gas, dust, and everything visible, makes up only a small fraction. Even dark matter, the invisible scaffolding believed to hold galaxies together, accounts for far less than dark energy. The implication is staggering. Most of the universe isn't made of anything we can touch or detect directly. It's composed of something that drives expansion but interacts with nothing in the ways matter typically does. This dominance raised immediate concerns. Was dark energy a real ingredient of the universe, or was it a sign that the equations describing cosmic expansion were incomplete? Scientists considered whether the acceleration could be explained by modifying the rules of gravity. If gravity behaved differently on large scales, perhaps weakening or shifting in unexpected ways, the acceleration might emerge naturally. In this scenario, dark energy wouldn't exist. It would be a sign that the framework needed revision. Some researchers found this idea appealing because it avoided introducing a new entity without direct evidence. If the rules themselves could be adjusted, the acceleration might become understandable within a unified picture. But altering the rules of gravity introduced its own challenges. Any new framework had to preserve the accurate predictions of Einstein's equations on small and moderate scales, while changing behavior only on cosmic scales. That task proved incredibly difficult. The existing equations describe planetary motion, black holes, and gravitational waves with precise accuracy. Any modification that altered cosmic expansion risked disrupting these successful predictions. The rules needed to shift subtly, becoming different only where distances became immense. Some theories attempted this by introducing additional fields or higher dimensional shapes of space, but these ideas were complex and difficult to test. Meanwhile, the simplest explanation, assign a constant energy to space itself, remained attractive because it required no adjustment to the underlying structure. Dark energy, under this interpretation, wasn't a substance but a feature of space. Its influence remained uniform and unchanging. Wherever space existed, dark energy existed. As space expanded, the total influence increased. This model matched observations well, but it came with a problem: the magnitude of dark energy. Theoretical predictions suggested that the energy of empty space should be enormous, far greater than the value measured. Instead, the observed amount was tiny, small enough to be almost negligible locally, yet large enough to dominate cosmic expansion. The discrepancy between predicted and observed values was so vast that it became one of the greatest unresolved gaps in modern physics. This mismatch raises a profound question. Why does dark energy exist at the level it does? Not too large, not too small, but precisely the amount needed to accelerate the expansion without disrupting everything else. Some speculate that the value might reflect something fundamental about the structure of the universe. Others consider the possibility that multiple universes exist with different energy levels, and ours simply happens to be one where the value allows galaxies and stars to form. These ideas remain speculative, but they highlight the depth of the mystery. Another interpretation of dark energy considers that its influence might not be constant. Instead, it might evolve over time. If dark energy changes subtly across cosmic history, the acceleration of the universe might vary as well. Early acceleration could differ from late acceleration. This idea opens new possibilities for understanding how the universe transitioned from deceleration to acceleration. But measuring whether dark energy changes is incredibly difficult. The signals are faint, subtle, and easily eclipsed by other cosmic effects. Scientists continue to examine distant supernovae, galaxy distributions, and cosmic background radiation for hints of change, but so far the results have remained inconclusive. Some observations have suggested that the expansion might not be uniform everywhere. Certain regions appear to expand slightly faster or slower than others. If true, this could imply that dark energy behaves differently depending on the distribution of matter or on the underlying structure of space. But the evidence remains uncertain, and researchers must navigate the challenge of distinguishing genuine cosmic variation from measurement artifacts. Instruments improve year by year, pushing observations deeper, but the puzzle remains intact. Despite the uncertainties, dark energy has become an essential component of modern cosmology. Without it, the observed universe makes little sense. Galaxies would not appear where they do. The large-scale structure would be mismatched. The timeline of cosmic evolution would be inconsistent. Even the shape of the cosmic background radiation would differ. Dark energy, as a concept, ties these observations together. But its success doesn't resolve the discomfort many scientists feel. The idea explains what the universe does, but not why it does it. It offers a description, not an understanding. The tension between description and understanding drives ongoing efforts to uncover the nature of dark energy. New satellite missions map the clustering of galaxies across vast distances, hoping to detect subtle signatures in the way structures form. Observatories measure supernovae with increasing precision, building a clearer picture of how the expansion has changed over time. Experiments analyze gravitational waves, looking for shifts in curvature that might reveal something about the fundamental framework. Even particle physics enters the discussion, searching for fields or interactions that could account for the outward influence. Yet despite the expanding network of approaches, dark energy remains an enigma. Its influence is undeniable, but its essence is invisible. It shapes the universe without revealing itself. It accelerates expansion without appearing directly in any detector. It changes the fate of the cosmos without offering clues about its origin. The ghost of dark matter already challenged the understanding of mass. Dark energy challenges the understanding of space itself. As the story of gravity develops, dark energy represents a turning point, a recognition that the universe refuses to behave according to the simple expectations once held. The acceleration forces a new perspective, not just on gravity, but on the nature of the environment that underlies everything. Whether dark energy is a real ingredient of the universe, a sign of incomplete rules, or the result of deeper structures shaping space, the mystery remains one of the most compelling in modern science. It pushes the exploration of gravity beyond falling objects and orbiting planets, and into the unseen patterns that guide the cosmos across billions of light years. Gravity gives the impression of being one of the most dependable features of the universe, something that behaves the same everywhere and follows rules that do not bend under pressure. You drop an object and it falls. You stand on the ground and feel its steady support. Satellites orbit Earth with predictable regularity. These everyday experiences create a sense that gravity is unwavering, a principle that doesn't wander or improvise. But that confidence comes from a narrow view, one shaped by familiar environments and ordinary scales. Once gravity is stretched across extremes, once it is tested near massive bodies, across vast cosmic distances, or in regions where matter thins to almost nothing, the supposed rigidity of its rules dissolves. Instead of a uniform force that behaves identically everywhere, gravity begins to look like something flexible, something shaped by circumstances, something capable of weakening, warping, or drifting away from the predictions that once seemed foundational. One of the earliest hints that gravity might not behave the same everywhere came from observations near compact objects like neutron stars. These stars pack immense mass into a tiny space, creating environments where curvature becomes far more intense than anything experienced near Earth. Objects falling near such stars do not follow the gentle arcs familiar from daily life. Their paths distort in ways that stretch the imagination. Light itself bends dramatically, wrapping around the star before emerging in directions that defy intuitive expectation. In these regions, gravity behaves not as a steady downward influence, but as a shaping of the environment so severe that ordinary motion ceases to resemble anything familiar. The rules aren't broken here, they're amplified to such extremes that they look like different rules entirely. But the behaviour isn't only dramatic near massive stars. Even modest astrophysical systems reveal that gravity changes character depending on scale. In galaxies, where stars orbit the centre at distances far beyond what the original equations were designed to handle, gravity appears stronger than expected. Stars move too quickly, the environment holds them more tightly than the visible mass should allow. This strong behaviour contrasts with the weakening predicted by traditional models. Instead of diminishing steadily with distance, the gravitational influence remains persistent, refusing to taper off as expected. The rules in these regions appear stretched, suggesting either an unseen contributor to the gravitational effect or a modification in how gravity behaves on large scales. This contrast between small-scale and large-scale behaviour raises a question that might feel unsettling. What if gravity follows different rules depending on context? On Earth, or within the solar system where mass is concentrated and distances are manageable, the equations work elegantly. But beyond this domain, in the vast spaces between stars or across the enormous structure of galaxy clusters, the predictions begin to drift from reality. This drift doesn't appear random. It follows patterns that might point to versions of gravity that deviate subtly from the traditional form. Another situation where gravity appears to wander from the expected behaviour occurs near extremely diffuse environments. In regions where acceleration drops to exceedingly low levels, far lower than anything experienced near Earth, the interaction appears to soften. Objects moving in these regions do not accelerate or respond to gravity in the same way as they do in stronger fields. This deviation suggests that gravity may not be linear across all ranges. Instead, it behaves as if reaching a threshold where its familiar form begins to shift. In such environments, even a small amount of visible mass influences motion more than expected, as if the environment responds with amplified sensitivity when gravitational fields become weak. These unusual behaviours have led some researchers to propose that gravity transitions between regimes. In one regime, where forces are strong and accelerations are high, the familiar rules hold. In another, where gravitational fields weaken and accelerations drop near zero, a different behaviour emerges. Under this view, the universe contains not one gravitational law but multiple, and the version we observe depends on the conditions present. This idea does not discard Einstein's framework. It simply adds complexity, suggesting that his equations might describe only one region of a larger gravitational landscape. Yet gravity doesn't merely weaken and strengthen across scales. It warps in ways that challenge the straightforward interpretation of curved space. In dynamic environments where mass moves rapidly, the curvature of space cannot remain static. It shifts, flexes, and responds in real time. These changes propagate outward as ripples, gravitational waves, which stretch and compress the environment as they pass. The detection of these waves confirmed that gravity is not a static field, but a dynamic one. Space behaves like a medium capable of transmitting disturbances, responding to changes in mass distribution even across vast distances. The rules governing these waves align with the framework Einstein proposed, but they also highlight how gravity behaves differently when pushed into dynamic regimes instead of static ones. In these contexts, gravity doesn't just shape motion, it becomes motion, carrying information across the universe. The existence of gravitational waves also raises another subtle point. If gravity can ripple, distort, and transmit information, then it is not rigid. It reacts. It shifts. It can be stirred by events and can propagate disturbances that reveal hidden features of mass, energy, and structure. This flexibility hints that gravity might be more variable and context-dependent than once thought. Black holes amplify this variability further. These regions of extreme curvature push the equations to their limits. Near a black hole, gravity no longer resembles a predictable influence. Time itself stretches, paths collapse inward, light bends into orbits, and at the central point, if the models are taken literally, curvature becomes infinite. That infinite curvature signals not physical reality but a failure of the existing theory. The framework cannot describe what happens at that centre. Gravity breaks down there, not because nature is flawed, but because the rules reach a domain where their assumptions no longer hold. A theory that describes the curve of space cannot handle its collapse into undefined extremes. Even outside black holes, the equations stumble in regions of high energy. When mass concentrates into forms dense enough to affect space profoundly, yet not quite collapse into a singularity, gravity becomes unpredictable. Models diverge. Paths become difficult to compute. Small changes in mass distribution can create exaggerated changes in curvature. These sensitivities reveal that gravity is not the clean, predictable system once imagined, but a phenomenon capable of becoming chaotic under the right conditions. Quantum mechanics introduces its own challenge. In the world of particles, forces arise from exchanges of discrete packets or interactions, not smooth curvature. Yet gravity refuses to fit this picture. It doesn't come with a clear particle of exchange, nor does it obey the same rules as the other forces. Attempts to quantize it, to force gravity into the quantum mold, have led to infinities, contradictions, and broken predictions. These failures highlight a fundamental inconsistency. Gravity behaves smoothly on human scales, but breaks down when pushed to scales where space-time itself becomes uncertain. In this domain, gravity wanders far from the script Einstein wrote, suggesting that it emerges from something deeper rather than existing as a fundamental entity. This tension grows even sharper in the early universe. Models of the young cosmos suggest that gravity must have behaved differently during the first fractions of a second. The rapid expansion that occurred, cosmic inflation, cannot be explained with gravity in its usual form. It required either a powerful temporary influence or a modification of gravity itself. When inflation ended, gravity resumed its familiar behaviour. The shift suggests that the rules may change not just across space but across time, altering as conditions evolve. Even the structure of space seems to hint at a gravity that adapts to its environment. In vast voids between galaxy clusters, gravity appears weaker not because mass is absent but because space expands more freely. In regions where mass accumulates, expansion slows. This interplay blurs the distinction between gravity and cosmic expansion. Instead of separate influences, they might be two expressions of the same phenomenon, gravity guiding structure locally, while expansion shapes motion globally. Under this interpretation, gravity doesn't weaken or strengthen arbitrarily. It responds to the density of its surroundings, shifting its character depending on whether the universe is crowded or empty. Some theories propose that gravity might emerge from the collective behaviour of microscopic components of space, similar to how temperature emerges from the motion of particles. Under this view, gravity is not fundamental. It's a byproduct of underlying interactions. In sparse environments, the collective behaviour changes. In dense environments, it shifts again. This would naturally produce different gravitational behaviours without requiring adjustments to the traditional equations. Gravity would wander off script because the script isn't fixed. It depends on the environment shaping it. This perspective also explains why gravity appears so weak compared to other forces. If it emerges from deeper structures, its strength might vary depending on the conditions of those structures. It would also explain why gravity integrates poorly with quantum mechanics. The two systems might not be describing the same layer of reality. One describes particles, the other describes the environment those particles inhabit. When pushed to extremes, the mismatch becomes obvious. These ideas offer different ways of interpreting the same observations. In some, gravity weakens or strengthens depending on scale. In others, it warps in response to mass and motion beyond the traditional framework. In others still, it emerges from deeper structures that shift with the environment. What all these interpretations share is the recognition that gravity does not always follow the familiar rules with the same grace across all contexts. The story that emerges is not one of a force misbehaving, but one of a theory reaching its limits. The rules work remarkably well within certain boundaries, but the universe does not restrict itself to those boundaries. When gravity steps beyond them, its behavior reflects not a flaw in nature, but a gap in understanding. The deviation from the script becomes a clue, a signal that the underlying structure of space, mass, and motion contains layers not yet captured by existing models. The fact that gravity weakens in some places, warps in others, and wanders off script across cosmic scales is not a failure of knowledge, but a sign that deeper truths are waiting to be uncovered. Truths that might unify the falling apple with the expanding universe and reveal the rules that shape everything in between. When people first began to imagine the universe as Einstein described it, a smooth, continuous fabric curving and flexing around mass, the idea felt elegant. It offered a picture of gravity that replaced invisible pulls with graceful geometry. It unified space and time into a single structure and gave scientists a reliable framework for describing planets, black holes, and the expansion of the cosmos. For many situations, this smooth fabric works beautifully, matching observations with precision. But beneath that calm exterior lies a domain where the description begins to break apart. When you shrink your attention down to the smallest scales, when you examine particles and the jittering energies that surround them, the quiet curvature described by Einstein dissolves. In its place emerges a chaotic realm where certainty evaporates, where motion becomes probabilistic, and where the environment itself seems to flicker. Gravity, in this microscopic world, refuses to follow the rules. This is where quantum mechanics begins to rebel against the smoothness of space-time. At the heart of the tension is a fundamental mismatch. Einstein's theory treats space as something continuous, something that bends rather than breaks, something that can be divided into infinitely fine points without losing meaning. Quantum mechanics, on the other hand, demands that nature behaves in discrete steps. It insists that energy, momentum, and even the states of particles come in tiny, indivisible pieces. The deeper you look, the more clearly the quantum view reveals itself. Particles don't follow definite paths. They exist in a cloud of probabilities. They fluctuate, appear, vanish, and reappear according to rules that defy classical expectations. In this domain, trying to apply the smooth curvature of space-time is like trying to draw a perfect circle using pixels. The basic ingredients don't match. This mismatch becomes obvious the moment someone tries to combine the equations that describe space-time with the equations that describe particles. The two systems refuse to merge. When physicists attempt to quantize gravity, turning the smooth curvature into something that follows the quantum rules, the results dive into infinities. The mathematics breaks down. Instead of yielding predictions, the equations collapse into undefined values. These failures highlight a problem that can't be ignored. The universe can't be described fully by smooth curvature alone, because the smaller scales don't allow smoothness. There must be something more. This tension reveals itself dramatically when scientists attempt to examine what happens at incredibly small distances much smaller than an atom, smaller even than the space between fluctuations in a field. At these scales, quantum mechanics predicts that energy fluctuates wildly. Virtual particles appear and vanish constantly. The environment becomes restless, never settling into a quiet state. These fluctuations would warp space-time continuously, producing an environment that cannot remain smooth. In Einstein's theory, space-time can bend but not flutter. In quantum mechanics, fluttering is unavoidable. The two descriptions collide sharply here, suggesting that the smooth fabric of space-time might be an illusion that works only when viewed from far enough away. Imagine trying to inspect the surface of a calm lake from a high vantage point. From that distance, the lake looks perfectly smooth, but step closer and you see ripples. Step even closer and you notice tiny waves on top of larger ones. Then you see disturbances created by the wind, the insects, the shifting currents below. The idea of a smooth surface evaporates. It wasn't smooth to begin with. It only appeared that way from far away. Something similar happens with space-time. At human scales, and even at planetary and stellar scales, it behaves smoothly. But zoom in far enough, and the illusions fall apart. The environment is not flat, it is turbulent. This turbulent view of space-time is often described as quantum foam, a term that tries to convey the agitation predicted by quantum theory. Instead of a continuous fabric, space-time would consist of constantly shifting, bubbling patches, ephemeral distortions that appear and vanish rapidly. These distortions would be too tiny and too short-lived to affect everyday motion, but they would dominate the fabric at the Planck scale, the smallest scale the universe allows. In this domain, Einstein's concept of curvature becomes meaningless. Geometry cannot be defined if the surface itself is restless. Distances, durations, and directions lose their certainty. In such an environment, the very idea of space-time as a smooth backdrop collapses. That collapse is what quantum mechanics demands, yet general relativity cannot accommodate. This conflict rises to the surface when considering black holes. These objects push space-time curvature to extreme levels, squeezing mass into regions so small that quantum fluctuations cannot be ignored. At the boundary of a black hole, the event horizon, the smoothness of space-time gives way to a stage where both quantum and gravitational effects become equally important. The rules begin competing. Quantum mechanics predicts a constant churning of particles and energy near the event horizon. General relativity predicts a calm, continuous boundary. In reality, neither description fully captures what occurs. The rebellion between the two becomes visible here, producing contradictions that physicists still struggle to resolve. This battle intensifies when scientists attempt to describe what happens at the very center of a black hole, where Einstein's equations predict a singularity, an infinitely dense point where curvature becomes infinite. Quantum mechanics rejects the concept of infinity in physical situations. It insists that there must be some limit to compression, some boundary that prevents infinite values. Yet without a theory that merges quantum mechanics with space-time curvature, no one can describe what lies at the center. The singularity represents not a feature of nature but a failure of the existing models. It is the clearest sign that the smoothness Einstein described cannot continue indefinitely. Another place where the rebellion emerges is in the early universe. During the first fraction of a second after the Big Bang, densities were enormous and fluctuations extreme. Quantum mechanics predicts that this environment was filled with chaotic energies and particles. General relativity predicts that space-time curved intensely. The combination creates conditions where neither theory alone is adequate. The smooth equations describing curvature break down. The quantum rules describing fluctuations break down. If we want to understand how the universe began, we need a theory that treats space-time as something that can behave both smoothly and irregularly, depending on scale. Without it, the first moments of the universe remain inaccessible. Some physicists suspect that space-time itself might not be fundamental. It could be something that emerges from deeper structures that behave according to quantum rules. In this interpretation, smooth space-time appears only when many underlying components interact, similar to how temperature emerges from the motion of countless molecules. Temperature isn't a property of a single particle. It exists only when many particles interact. If space-time works the same way, its smoothness would disappear when examined closely, because the underlying elements do not themselves form a smooth environment. This idea treats gravity not as a fundamental force, but as a manifestation of deeper principles. Under this view, the quantum rebellion isn't a problem, it's a clue. Other approaches attempt to quantize spacetime directly by imagining it as a network of discrete units. These units might connect like the links of a chain or the nodes of a graph. They might follow probabilistic rules rather than geometric ones. In these models, smooth curvature arises only when many units act together. The environment would appear smooth at large scales, but granular at small scales, resolving the tension between the two theories. But these ideas, while promising, remain speculative because the structures they propose operate at scales far too small for any current technology to observe. The rebellion continues unresolved. Even when scientists attempt to bridge the gap by treating gravity as another force mediated by particles, the effort reaches a dead end. Every other force in nature is carried by particles: photons for electromagnetism, gluons for the strong force, U and Z bosons for the weak force. If gravity were similar, it would require its own carrier particle, often referred to as the graviton. But attempts to model gravitons within the quantum framework lead to contradictions. The particle would interact in ways that break the equations. It would produce effects that don't align with observation. Worse, the smallest disturbances in curvature, if treated as quantum particles, would produce energies so large that they collapse into black holes. The mathematics spirals out of control. Even experiments hint at the problem. When researchers measure time at extremely precise scales, the flow of time appears smooth, but only down to a point. Below certain thresholds, the uncertainty grows, suggesting limits in how finely time can be measured. Similar limits appear in measurements of distance. The more precisely you try to measure a tiny length, the more uncertain the result becomes. This is another sign that the quantum world resists being forced into smooth geometric descriptions. The rebellion isn't hidden. It appears everywhere we look closely enough. The struggle between these two views, smooth space-time and jittering quantum reality, has shaped some of the deepest questions in modern physics. The search for a theory that unites the two has generated ideas that push imagination to its limits. Multi-dimensional spaces where gravity leaks into hidden dimensions, strings vibrating in higher dimensions, holographic principles suggesting that the universe might be a projection from a deeper, lower dimensional system. Each idea attempts to bridge the gap. Each offers a piece of the puzzle, yet none have resolved the rebellion fully. Part of the reason this conflict feels so difficult is that the smoothness of space-time is something experienced intuitively. When you walk, sit, or reach for something, you assume the ground beneath you is stable and continuous. You assume time runs in a steady rhythm. These assumptions work perfectly at everyday scales, but intuition doesn't extend to the quantum world. There, certainty evaporates, smoothness dissolves. Even the concept of location becomes slippery. A particle doesn't sit in one place until measured. A path doesn't exist until defined. The environment itself is part of the probability. Everything is too lively to be smooth. This animated, probabilistic view is completely at odds with the unbroken curvature Einstein described. Yet the universe contains both realities. One governs the large-scale structure of galaxies and stars. The other governs the behavior of particles and fields. The conflict between them isn't a flaw in either theory. It's a sign that both are parts of a larger picture not yet visible. This larger picture might reveal that smooth space-time is an approximation, much like how solids appear rigid until viewed closely enough to reveal their atomic structure. It might reveal that quantum fluctuations are not disruptions, but the foundational elements from which space-time emerges. Or it might show that the two systems merge not by adjusting one or the other, but by revealing a deeper layer that gives rise to both. What's clear is that the rebellion of quantum mechanics against the smoothness of space-time isn't a temporary inconvenience. It's one of the most significant clues about the nature of the universe. It marks the boundary where current understanding reaches its limit. It highlights the need for a new framework capable of describing not just how gravity curves space or how particles fluctuate, but how both arise from the same underlying principles. The universe has offered hints through black holes, gravitational waves, cosmic expansion, and particle behavior. Each hint points to a future understanding where the rebellion disappears, not because one theory conquers the other, but because both find their place within a broader unified picture. The path toward that picture remains open, shaped by questions that continue guiding the exploration of gravity, motion, and the invisible structure of the universe. When scientists describe gravity in simple terms, they often say that all objects fall the same way regardless of their mass. You can drop a feather and a hammer on the moon, and they hit the ground at nearly the same time. You can roll different spheres down the same slope and watch them accelerate in unison. These demonstrations suggest a comforting certainty. Gravity treats everything equally. The rules don't pick favourites. Yet once you shift from everyday objects to the microscopic world, this equality becomes harder to maintain. Particles that should behave identically in theory begin showing differences in the way experiments treat them, the way equations describe them, and the way thought experiments imagine them. The idea that everything falls the same way becomes complicated once the smallest ingredients of reality enter the picture. The deeper you look, the more sharply the divide appears between what theory says should happen and what certain interpretations of nature suggest might be possible. The first layer of this divide comes from the classical view. According to Einstein, objects follow paths shaped by the environment around them. The equations describing these paths don't care about the mass of the object. They care only about the curvature of the surroundings. Under this framework, all objects with mass follow the same natural trajectory through the environment. This principle, often called the equivalence principle, became one of the pillars supporting modern gravitational theory. It's elegant, reliable, and confirmed across countless experiments involving macroscopic objects. But when the experiments shift toward particles and fields, the situation becomes far less clear because the tools used to describe particles don't align neatly with the tools used to describe curvature. Quantum mechanics treats particles as entities that exist in states, not as small billiard balls with definite paths. A particle doesn't travel along a single trajectory until measured. Instead, it spreads across a range of possibilities. It occupies a distribution of states influenced by probability rather than certainty. Asking how such a particle falls becomes challenging, because it doesn't fall in the usual sense. It evolves according to equations that incorporate mass, energy, and information in ways that don't directly correspond to the smooth curvature of spacetime. These differences suggest that while macroscopic objects fall cleanly through curved space, particles fall through a landscape shaped by quantum rules, where curvature might play a role but doesn't dominate the narrative. One of the earliest puzzles appeared when scientists examined how different types of particles respond to gravitational influence. Under classical assumptions, particles with different properties should follow identical trajectories if placed in the same environment, but quantum particles come with additional characteristics, spin, charge, internal structure, that influence their behavior. Some particles interact with fields in ways that cause subtle differences in motion. For example, charged particles respond not only to gravity but also to electromagnetic fields, which complicates any attempt to observe pure gravitational behavior at the particle level. These overlapping influences make it difficult to test whether particles truly fall identically, because isolating gravity from everything else is nearly impossible at such small scales. At the same time, theory insists that gravity should affect all forms of energy equally. Since mass and energy are equivalent under Einstein's equations, even massless particles like photons should respond to curvature. This idea explains why light bends near massive objects. But does that bending mean that photons fall in the same sense that objects with mass fall? The answer depends on how you interpret the path of a photon. It travels at a constant speed, but its direction changes because the geometry of space changes. The bending is predictable, yet it isn't identical to the behavior of particles with mass. The speed never varies, and the interaction doesn't reflect acceleration in the traditional sense. The result is that while theory claims everything falls equally, the details of how massless and massive particles respond reveal distinctions that are difficult to ignore. Another complication arises when considering how different forms of energy experience time. If time flows differently in regions with varying curvature, then particles with different internal dynamics might experience these changes differently. A particle that oscillates internally, like one with a defined frequency, might evolve differently from one without such structure when placed in regions of varying gravitational potential. These differences don't violate the equivalence principle directly, but they highlight subtleties in how particles experience the environment. The principle applies to trajectories, not to internal processes. When internal processes respond differently to the surroundings, the behavior of particles becomes less uniform. Experiments designed to test these differences often involve comparing the behavior of particles in regions of varying gravitational potential. In one type of experiment, researchers observe how atomic clocks behave when placed at different heights. The higher clock runs slightly faster. This result is consistent with Einstein's theory, but it also demonstrates that time itself dilates depending on position. At the particle level, this time dilation affects the evolution of quantum states. Some states shift more noticeably than others. If different particles or systems respond differently to these shifts, then their behavior might appear to diverge even if they follow the same trajectory. This creates a sense that particles fall differently, not in their position but in their internal evolution. Another line of inquiry examines how particles behave when placed in free fall. According to the classical view, a particle in free fall experiences no gravitational force. Yet quantum experiments reveal that particles still show phase shifts when placed in free-falling systems. These shifts depend on the gravitational potential, suggesting that particles retain memory of the environment even when forces have been removed. This behavior doesn't fit neatly into the classical idea of falling. Instead, it hints that particles respond to gravity in ways more nuanced than simple trajectories. They feel gravity not through force but through the geometry of the environment affecting their internal states. This area becomes even more interesting when theorists consider particles that possess different types of mass. In classical physics, mass is a single concept, the amount of matter in an object, but in quantum field theory, mass becomes layered. There is inertial mass, which measures resistance to acceleration, and gravitational mass, which measures how strongly an object responds to gravitational influence. These two concepts are assumed to be equivalent, but quantum theories treat mass as something that emerges from interactions with fields rather than as an inherent property. If mass arises from these interactions, could different particles acquire mass in ways that affect how they respond to gravity? The framework suggests yes, though experiments have not yet confirmed any deviation between inertial and gravitational mass. Still, the possibility remains open, and the theory invites questions that classical physics never had to consider. Another aspect of this divergence appears in the way quantum particles tunnel through barriers. In classical physics, an object cannot pass through a barrier unless it has enough energy to overcome it. In quantum mechanics, a particle can appear on the other side of a barrier even without sufficient energy. This tunneling doesn't violate energy conservation. It reflects the probabilistic nature of quantum systems. But how does tunneling respond to gravitational influence? Does a particle tunnel differently depending on the curvature of the environment? Some theories suggest that gravity might influence the tunneling probability by altering the shape of the potential landscape. If so, then the way particles move through space would depend not only on mass and energy, but on how the environment bends. This modification hints at differences in how particles fall, depending on their surroundings and internal properties. The divergence continues when looking at neutrinos. These particles are extraordinarily light, travel near the speed of light, and oscillate between different forms. Because they interact weakly with matter, they can pass through planets with ease. Their oscillation behavior depends on distances, energies, and phases. Some theorists propose that gravitational environments might influence their oscillations subtly. If curvature affects these oscillations, then neutrinos could behave differently depending on where they travel. This would mean that particles with identical masses and energies might fall differently depending on internal states, adding yet another layer of complexity. Even photons, which are massless and simple in classical terms, acquire complexity in quantum settings. Their behavior depends on polarization, wavelength, and interactions with fields. Gravity bends their paths, but some models suggest that different frequencies might experience slightly different curvature under certain conditions. Although this effect is extremely small and not yet observed, it introduces the theoretical possibility that massless particles might not all fall exactly the same way. These tiny differences, if confirmed, could open a new direction in understanding gravity as something influenced by more than simple curvature. Another important distinction emerges from thought experiments involving quantum superpositions. If a particle exists in two positions at once, how does it fall? Does each component of the superposition follow a separate path through curved space? Or does gravity collapse the superposition by selecting a single trajectory? Some interpretations suggest that gravity might play a role in collapsing quantum states, forcing the system to choose a definite configuration. If this is true, then particles in superposition behave differently from ordinary objects. They fall in multiple ways simultaneously until an interaction forces a single outcome. This possibility challenges the equivalence principle by suggesting that quantum states influence how objects respond to gravity. Further complications appear in attempts to unify gravity with the other forces. The strong, weak, and electromagnetic interactions all behave consistently under quantum rules. They work through exchange particles. They follow the same mathematical principles. But gravity refuses to join this framework. It doesn't fit cleanly into the quantum mold. This resistance suggests that gravity might treat particles differently than other interactions do. It might interact with fields rather than with particles directly. Or it might emerge from deeper structures that shape particle behavior indirectly. In either case, the theory of how particles fall becomes entangled with the nature of gravity itself. Some researchers have explored whether gravity might differentiate between particles that carry different types of energy. A particle's total energy includes rest mass, kinetic energy, and potential energy. If gravity responds to these components in different ways, then particles with identical masses but different kinetic energies might fall differently. The theory doesn't exclude this possibility outright, though observations in everyday settings show no deviation. The question remains open in extreme environments, such as near black holes or in early universe conditions. Theoretical frameworks also explore whether particles with different spins might couple to curvature differently. Spin is a quantum property with no classical analogue. It influences how particles behave in magnetic fields and how they interact with other particles. Some models suggest that curvature could couple to spin, altering the path of spinning particles slightly. These effects would be extremely small, yet they point to another potential distinction between how different particles fall. Even hypothetical particles become part of this discussion. Some theories propose new particles that interact only through gravity or only through quantum fields. If such particles exist, their behavior in curved space could differ significantly from the familiar particles in the standard model. These differences wouldn't violate the universality of gravity at macroscopic scales, but they might break the symmetry at quantum levels. All these possibilities shape a picture where particles behave in ways that challenge simple interpretations. The classical idea that everything falls equally becomes less certain. The quantum world introduces internal properties, probabilistic evolution, subtle interactions, and context-dependent behavior. These differences don't overthrow the equivalence principle. They suggest that the principle applies most cleanly in the macroscopic realm, but that its meaning becomes murkier when applied to states that do not follow definite trajectories. Yet the lack of clarity is not a problem, it is a guide. Every difference that arises between theory and thought pushes the exploration further. These divergences reveal the boundaries of existing understanding and mark the areas where the next breakthroughs may emerge. Whether particles fall differently in measurable ways, or whether the differences remain confined to abstract theory, the tension highlights something important. Gravity may not be a single story told the same way across all scales. It may be a narrative that shifts depending on the context, revealing layers that classical descriptions cannot capture and quantum descriptions cannot ignore. The idea that gravity might not be the complete story has lingered in scientific discussions for decades, but the more researchers examine the universe, the stronger that suspicion becomes. Each unexplained observation invites a new question. Each gap between prediction and reality hints that something important is still missing. And because gravity touches every structure, every motion, and every corner of the cosmos, any missing element, whether a force, a particle, a mechanism, or a deeper framework, would reshape the understanding of everything from falling objects to the expansion of the universe itself. The challenge lies in deciding whether the unexplained behaviour comes from something new, acting in the background, or whether the current story of gravity is incomplete in ways scientists have not yet discovered. One of the earliest and most enduring clues came from the rotation of galaxies. The speeds at which stars orbit the centres of galaxies never match the predictions based on visible mass. Instead of slowing at larger distances, stars continued moving rapidly. This discrepancy raised questions about whether a hidden ingredient was present. For a long time, dark matter filled that role. It provided the extra gravitational influence needed to explain the motions. But dark matter came with a problem. It was invisible, undetected, and defined entirely by its absence of interaction with light. Introducing it solved the equations but didn't explain what it was. Many embraced it as the simplest answer, but others wondered whether the need for it pointed not to hidden mass but to hidden rules. This uncertainty grew as more evidence accumulated. Galaxy clusters exhibited the same discrepancy, requiring far more mass than what could be seen. The formation of large-scale structures across the universe seemed too rapid without dark matter's influence. Yet even with dark matter included, anomalies remained. Some small galaxies didn't behave as expected under the dark matter framework. Some large galaxies showed rotation curves that aligned too neatly with visible mass, as if their behaviour depended more on the material that could be seen than on any invisible halo. These inconsistencies hinted that perhaps the missing element wasn't a substance but a principle, something that changed how gravity acted at different scales. The puzzle deepened when cosmic expansion entered the discussion. Observations of distant supernovae showed that the universe was accelerating, not slowing. Gravity, under the standard model, could not cause acceleration. To address this, dark energy became the next hidden ingredient. Like dark matter, it wasn't discovered directly. It was introduced to explain behaviour that didn't align with existing rules. Dark energy provided an outward influence, pushing galaxies apart and stretching space itself, but the introduction of both dark matter and dark energy led to an uncomfortable recognition. Most of the universe seemed to be made of things that could not be seen, measured, or interacted with, except through their effects on gravity. This situation forced scientists to confront a possibility. What if the missing elements weren't entities but consequences of a deeper story? What if gravity, as currently understood, was only a partial description of a larger framework? The notion that gravity might change depending on scale gained traction. Some theories propose that gravity behaves differently when accelerations become extremely small, as in the outskirts of galaxies. Others suggested that space itself might have different properties depending on density. These ideas weren't widely adopted at first, because the dark matter explanation offered a cleaner, more conventional approach. But the persistence of unexplained behaviour prevented alternative views from fading. Beyond galaxies and cosmic expansion, other clues began emerging from unexpected places. For example, some experiments revealed that the behavior of particles under gravity differed subtly from theoretical predictions. These differences weren't large enough to disrupt the entire framework, but they were consistent enough to raise questions. If particles interacted with gravity differently depending on the internal states or energy levels, then the force might not be uniform across all scales. The search for a unified theory that merges gravity with quantum mechanics intensified, because the inconsistencies suggested that the two frameworks were not independent but interconnected in ways not yet understood. One line of inquiry proposed that gravity might not be a fundamental force at all. Instead, it could be an emergent property, a consequence of more basic interactions beneath the surface. Under this view, gravity is not a primary influence but a secondary effect, arising from deeper principles governing information, energy, or the structure of space. If this interpretation is correct, then the anomalies observed in galaxies and cosmic expansion might not require new forces or new particles. They might indicate that the emergent rules change under certain conditions. In such a scenario, the universe's large-scale behavior would differ from its small-scale behavior, not because new ingredients appear, but because the foundational interactions produce different emergent effects depending on the environment. This idea of emergence opens the door to another possibility. Perhaps the missing story involves the nature of space-time itself. Most modern theories treat space as a continuous, smooth entity, curving in response to mass. But quantum mechanics suggests that the smallest scales cannot be smooth. Instead, they are turbulent, filled with fluctuations. If space-time emerges from underlying quantum states, then gravity might reflect the behavior of those states rather than the smooth geometry they create at larger scales. This could explain why gravity becomes difficult to unify with the quantum framework, because the smooth description is an approximation, not a fundamental truth. If the underlying structure of space-time behaves differently in different regimes, the gravitational rules derived from it would also shift. Additionally, some theories explore the idea that extra dimensions might shape gravity in ways not visible in everyday life. If additional dimensions exist beyond the familiar three of space and one of time, their influence might be subtle, locally, but profound on cosmic scales. Gravity could leak into or interact with these hidden dimensions, weakening or strengthening depending on distance. This idea provides another potential explanation for galaxy rotation curves and cosmic acceleration. The familiar rules of gravity might be incomplete because they describe only the four-dimensional projection of a higher dimensional system. These possibilities, emergent gravity, hidden dimensions, scale-dependent rules, set the stage for a deeper question. Is it more likely that the universe contains unseen forces and particles, or that the understanding of gravity is missing a fundamental component? The answer varies depending on the evidence examined. For some phenomena, adding dark matter solves the problem elegantly. For others, modifying gravity produces better alignment. The tension between these approaches reveals that no single explanation fits every observation perfectly, reinforcing the idea that something deeper remains hidden. This deep story might also involve interactions not captured by any current theory. Some researchers have proposed that gravitational influence could arise from entanglement between quantum states across vast distances. Under this view, gravity emerges from correlations rather than forces. If these correlations vary depending on the distribution of matter or the geometry of space, the resulting gravitational effects would also vary. This approach shifts the understanding of gravity from a geometric or force-based interpretation to an informational one. It suggests that the universe might be structured in ways where relationships between particles determine the shape of the environment itself. Another idea suggests that gravity might interact with fields that haven't yet been discovered. These fields could influence motion subtly, adding contributions that mimic the effects of dark matter or dark energy. If such fields exist, they could operate in areas where matter is thin, producing behavior that deviates from predictions. This idea frames the anomalies not as failures of gravity, but as signs of missing interactions. Some models propose that the universe might not be uniform at the larger scales. If its structure varies more significantly than assumed, the equations describing cosmic expansion might need revisions. The observed acceleration could result from spatial variations rather than a new form of energy. This interpretation avoids introducing dark energy altogether, replacing it with more complex initial conditions or structure formation. But this approach requires rethinking the distribution of matter and curvature, making it challenging to reconcile with the simplicity of current models. One of the most intriguing possibilities is that the missing story involves time itself. If time flows differently depending not just on curvature, but on some deeper property of the environment, then the behavior of galaxies and cosmic expansion might reflect temporal distortions rather than hidden forces. This idea is still speculative, but it emphasizes how intertwined gravity is with the concept of time. The more these possibilities accumulate, the clearer the challenge becomes. Either gravity includes more than the current framework describes, or the universe contains elements not yet seen. In both cases, the situation feels similar to earlier moments in scientific history, when paradigms shifted because anomalies could not be ignored. The precession of Mercury led to general relativity. The ultraviolet catastrophe led to quantum mechanics. The unexplained rotation of galaxies, the accelerating expansion of the universe, the mismatch between gravity and quantum systems. These modern puzzles may be the clues that guide the next major shift. What makes the current moment especially compelling is that the puzzle does not reside in a single observation, but in a pattern of inconsistencies across many scales. Small-scale phenomena challenge quantum descriptions. Large-scale structures challenge gravitational descriptions. Intermediate phenomena challenge both. The idea that a single missing element could resolve all these inconsistencies is appealing, but the universe rarely provides simple answers. Instead, the hidden story may involve multiple layers, some involving forces, some involving fields, some involving the structure of space, and some involving principles not yet imagined. As theories evolve, the possibility that a hidden force might exist remains open. Such a force would need to act subtly, influencing behavior without contradicting established results. It would need to shape galaxy rotation without disrupting solar system dynamics, guide cosmic expansion without altering local environments, and unify with quantum systems without producing contradictions. Finding such a force would require precision measurements that probe the boundaries between classical and quantum behavior. At the same time, the possibility of a hidden story grows stronger. The universe may not be governed by simple extensions of the existing framework. It may be governed by principles that render the current descriptions as approximations. Those approximations hold well in certain regimes, but break in others, revealing the edges of understanding. These edges, dark matter that remains elusive, dark energy that remains mysterious, quantum properties that resist classical interpretation, cosmic structures that defy assumptions, form the outline of the deeper story. Whether that story includes a new force or a new framework, it promises to reshape the understanding of gravity from something familiar into something profoundly more complex. The exploration continues because every anomaly becomes a clue, every mismatch becomes a direction, and every unanswered question becomes an invitation to push further into the unknown, a process that has always guided science toward its next revelation. Gravity is so woven into everyday experience that imagining a universe without it feels almost impossible. The mind resists the thought at first, because gravity provides a sense of stability so constant that it becomes invisible. It shapes the ground you stand on, the arc of a falling object, the motion of planets, and the clustering of galaxies. It is the quiet framework underlying nearly every familiar structure. But the more scientists explore its mysteries, how galaxies spin, how the universe accelerates, how particles behave differently depending on scale, the more reasonable it becomes to ask a difficult question. What if gravity, as currently understood, isn't the fundamental influence it appears to be? What if the universe could exist without gravity as it's now described? And if so, what would that universe look like? The answer is not simply the absence of a force, it's the presence of a different way for structure to form, a different kind of environment shaping motion, and a different relationship between matter and space. To imagine such a universe, it helps to question what gravity actually does. At the most familiar scale, it appears to pull objects together. At planetary and stellar scales, it binds systems and holds orbits in place. At galactic scales, it shapes rotation and clustering. At cosmic scales, it competes with expansion. But each of these roles might not require a single unified influence. If structure can emerge from other interactions, if space can behave differently depending on context, or if mass influences motion in ways unrelated to curvature, then gravity as it's currently defined might not be necessary. The picture becomes one where gravity is not a universal force, but one interpretation of a deeper set of principles. One way to imagine a universe without familiar gravity is to consider a scenario where space doesn't bend around mass. Instead of curvature dictating motion, objects might follow trajectories determined by entirely different interactions. In such a setting, mass wouldn't warp the environment. Light wouldn't bend around stars. Orbits as understood in the classical sense wouldn't exist. Instead, structure would require something else to act as the stabilizing influence. Perhaps another field permeates the universe, guiding the arrangement of matter through interactions unrelated to geometric distortion. This hypothetical field might not resemble anything known. It might attract under one set of circumstances and repel under another. The point is not to propose a specific replacement, but to recognize that curvature is only one possible explanation for structure. The absence of familiar gravity would also change the experience of motion. In a universe shaped by pure inertia, objects would travel in straight paths unless acted upon by other forces. Without curvature, these straight paths wouldn't be distorted by the presence of mass. Motion would become a negotiation between inertia and whatever new interactions replace gravitational influence. Systems could still form if these interactions allowed them, but the shapes and behaviours of those systems would be different. Planets as recognised today might not form at all unless a new mechanism allowed mass to cluster. Stars might require different rules to ignite. Galaxies might never resemble spirals, ellipses, or irregular clumps. The universe would be structured, but its structure would follow unfamiliar patterns. Another way to imagine such a universe is to consider that what's currently called gravity might be an emergent effect rather than a fundamental one. Under this interpretation, the bending of space is only a convenient way to describe what happens when vast amounts of underlying microscopic behaviour combine into a smooth pattern. At large scales, that smoothness might create the illusion of curvature, while at smaller scales different rules apply. If the emergent behaviour changed, the curvature could disappear. What would remain is the underlying system, a set of interactions between basic components of reality. These components might produce effects similar to gravity in many situations, but differ dramatically in others. Under this view, the universe wouldn't be without gravity entirely. It would be without the familiar gravitational interpretation. The environment would still shape motion, but the shaping would come from deeper mechanisms. This perspective becomes especially interesting when considering the quantum world. Quantum mechanics doesn't require gravity to function. It operates through probabilities, superpositions, and interactions that don't involve curvature. If gravity were removed from the classical picture, quantum rules would remain intact. The universe might still form atoms, molecules, chemical reactions, and biological structures. All these processes rely on electromagnetic, nuclear, and quantum interactions. Gravity contributes nearly nothing to atomic structure. Its influence becomes noticeable only at large scales. Removing the familiar gravitational interpretation would therefore change the cosmic landscape but not the microscopic one. A universe without gravity as currently known could still contain matter and energy, but the arrangement of that matter would be determined by different rules. For example, clusters of particles might form because quantum interactions allow them to bind. Stars might not require gravitational compression to ignite, but could rely on entirely different mechanisms for generating heat and radiation. The resulting stars might behave differently, shine differently, or live for shorter or longer periods depending on the rules guiding their formation. The diversity of structures could potentially expand or collapse depending on whether these alternative mechanisms were stable. Cosmic expansion would also change. In the current understanding, the expansion of the universe reflects a balance between gravitational influence pulling matter inward and dark energy pushing space outward. Without gravitational curvature as described, expansion might proceed uniformly. It might accelerate or decelerate based on rules unrelated to mass. Space could stretch because of intrinsic properties not tied to matter. Such expansion might create regions of high density and low density without gravity's involvement. The universe could become patchy or uniform depending on the behavior of these properties. This shift highlights that expansion doesn't require gravity. It requires a mechanism for distance to increase. Gravity shapes how matter moves within that expansion, but eliminating it doesn't prevent expansion itself. One of the striking implications of a universe without gravity is that concepts like black holes, event horizons, and gravitational time dilation would disappear. These phenomena rely on curvature. Without curvature, regions of collapse wouldn't form in the same way. Mass might accumulate, but it wouldn't create horizons where time stretches indefinitely, or paths bend inward permanently. The dramatic features that dominate discussions of extreme environments would be absent. Instead, new extreme phenomena could arise from the alternative mechanisms governing motion. These phenomena might be just as dramatic, but they would follow patterns unfamiliar today. The absence of familiar gravity also invites questions about time. In Einstein's theory, time flows differently depending on curvature. Without curvature, time might become uniform across the universe. But other mechanisms could still cause variations. Quantum fluctuations, interactions with fields, or changes in density could influence the flow of time in ways not related to curvature. The idea that time depends on environment wouldn't disappear. It would simply gain a new interpretation. Instead of bending with space, time might stretch or compress depending on conditions at the microscopic level. Another scenario involves the possibility that gravity is not removed entirely, but replaced with a force that behaves differently under different conditions. This new influence might act like familiar gravity at small scales, but diverge at large ones. The divergence could eliminate the need for dark matter or dark energy by providing a new interpretation of galaxy rotation and cosmic expansion. In such a universe, gravity wouldn't disappear. It would transform. It would become a different kind of interaction, one that produces similar effects in familiar contexts but diverges where the current theory struggles. This transformation would maintain planets, stars, and galaxies, while reshaping the anomalies that currently challenge understanding. This possibility aligns with theories that introduce new fields interacting with mass. These fields might guide motion in ways that resemble gravity but stem from different principles. They could interact strongly at one scale and weakly at another. They might push instead of pull or respond to density rather than mass. In such environments, what appears to be gravitational attraction today might be the result of deeper interactions tomorrow. The familiar story of gravity bending space might be replaced with a story of fields shaping motion through different mechanisms. Imagining a universe without gravity as currently known also highlights the role gravity plays in the formation of structure. Without it, the distribution of matter would depend on interactions at other levels. Quantum fields might encourage clustering based on resonance rather than attraction. Particles might gather due to local interactions rather than long-range influence. The cosmic web, the large-scale structure of filaments and voids observed today, might not exist. Instead, new patterns would arise shaped by rules unrelated to curvature. These patterns could be simpler or more complex depending on how the alternative interactions behave at large scales. This thought experiment also reveals the flexibility of cosmic possibilities. If the universe had different laws governing large-scale motion, the structures that emerge could be so unfamiliar that they defy easy description. Instead of stars forming from collapsing clouds of gas, energy might concentrate in localized excitations of fields. Instead of planets forming from accretion, stable configurations might arise from resonant states. The narrative of cosmic evolution would change entirely, guided by principles unrelated to gravity. Part of the appeal of imagining such a universe is that it reveals how much the current understanding of gravity depends on interpretation. The bending of space describes what's observed, but it might not reflect the underlying reality. Another framework could exist that produces identical observations, yet describes the environment differently. The success of Einstein's equations doesn't prevent alternative explanations. It simply establishes a standard that any new framework must match at the scales where Einstein's theory excels. This requirement allows for a different kind of universe, one where gravity is not a force, not curvature, not an emergent effect, but something entirely else. It could be a statistical behavior arising from thermodynamic principles. It could be a manifestation of information flow in quantum systems. It could be a response of space to changes in entanglement patterns. Each of these ideas constructs a universe where familiar gravity doesn't exist, but structure still emerges. Motion still has direction. Time still flows. The cosmos remains coherent even if the explanation changes. The exploration of such a universe does not diminish the importance of gravity. It highlights how deeply gravity shapes thought. Removing it forces a re-evaluation of every assumption about how the universe works. But imagining its absence isn't an attempt to undermine its role. It is an attempt to recognize that the understanding of gravity may be provisional. The familiar picture might be a layer covering deeper structures waiting to be uncovered. A universe without gravity as currently known is not a universe without order. It is a universe where order arises differently. It is a universe shaped by interactions that don't rely on curvature. It is a universe where motion follows rules that might feel alien but remain consistent. And it is a universe that invites reflection on whether the familiar interpretation is the final word or merely the beginning of a deeper story. These thought experiments serve as reminders that gravity, as powerful and pervasive as it seems, might not be the ultimate explanation. The universe might obey principles that transcend curvature, attraction, and force. Those principles could reshape the view of everything: matter, motion, time, and the vast expanse that contains them. Imagining a universe without gravity as it's now described is not an act of removing a concept. It's an act of reaching toward a deeper level of understanding, where the familiar gives way to what the universe has yet to reveal. Rethinking the force that holds everything together begins as a quiet exercise in curiosity, but it quickly becomes something more demanding. Gravity has always felt like the most grounded of all ideas, the one influence that doesn't hide behind complex equations or exotic concepts. It pins your feet to the floor, guides the path of a thrown object, shapes the arc of the moon, and keeps planets in their orbits. It's dependable in ways few natural principles are. Yet when the familiar comfort of that understanding is set aside, and the universe is examined through the lens of its deepest puzzles, the unexpected spins of galaxies, the accelerating expansion of space, the resistance of quantum mechanics to smooth geometry, the confidence begins to fade. What emerges is a picture where gravity might not be what it has long seemed. And rethinking that force means rethinking not only how matter moves, but how reality itself is structured. The first step in this reconsideration involves acknowledging something difficult. gravity explains a great deal, but not everything. Even within the environments where it works beautifully, the explanations rely on assumptions that rarely get examined. When you drop an object and watch it fall, you're seeing only the most basic expression of the principle. But that simplicity hides the fact that the equations describing the fall assume the environment is smooth, that space behaves consistently, and that mass interacts with curvature in a predictable way. These assumptions appear harmless because they work, but the moment they're stretched across cosmic distances or pressed into quantum scales, they reveal their limits. Rethinking gravity requires facing those limits without dismissing the success that came before. Part of what makes this process challenging is that gravity has a long history of appearing complete before revealing it wasn't. Newton's description worked so well that it became unquestioned for centuries. It guided everything from cannon trajectories to planetary motion. But Mercury's orbit refused to cooperate fully, bending the rules just enough to show that something was missing. Einstein arrived with a transformation so profound, it felt like a different language. Instead of imagining gravity as a force, he described it as the shape of the environment itself. Space and time became a single interwoven structure. Objects followed natural paths through curved environments, rather than being tugged invisibly by distant masses. This reinterpretation reshaped the understanding of nearly everything. Yet even Einstein's successful model didn't capture the full story. The deeper the exploration went, the more inconsistencies emerged. Rethinking gravity means confronting the idea that Einstein's framework, while elegant, might also be an approximation of something deeper. It means acknowledging that the smooth curvature he described might arise from conditions that only look continuous when examined from far enough away. At smaller scales, the fabric might be turbulent. At larger scales, the behavior might diverge. Gravity, instead of being a universal rule, might be a contextual one, strong and predictable in familiar environments, but transformed or incomplete in others. This realization doesn't diminish Einstein's achievement. It places it within a broader story, one where theories evolve because the universe insists on revealing more complexity than expected. Each failure of prediction becomes an opportunity, each mismatch a doorway. But stepping through that doorway requires letting go of the idea that gravity is a single, simple influence. One of the clearest reminders of this need comes from the issue of scale. Gravity behaves consistently within the solar system. It predicts orbits, tides, and motion with remarkable accuracy. But galaxies don't follow those same rules. Their stars orbit too fast. Their shapes remain stable when equations say they should disperse. The standard explanation introduces invisible mass, dark matter, but doing so raises the uncomfortable possibility that the theory might not be wrong, just incomplete. It's an important distinction. Incompleteness allows for refinement. It invites new ideas rather than erasing old ones. The same issue appears on cosmic scales. Expansion accelerates. Structures form faster than expected. The introduction of dark energy fills the gap mathematically, but it doesn't explain why the expansion behaves in that particular way. The equations work once new ingredients are added, but relying on large unseen components suggests something deeper might be missing. A complete theory shouldn't need placeholders the size of the entire universe. Rethinking gravity means questioning whether these placeholders represent actual entities or signs that the fundamental framework is insufficient. Another part of this process involves recognizing the tension between gravity and quantum mechanics. These two descriptions of nature have lived side by side for a century, each successful in its own domain, yet incompatible when brought together. Gravity requires smoothness. Quantum mechanics requires granularity. Gravity requires definite paths through curved environments. Quantum mechanics allows objects to exist in multiple states simultaneously. The problem isn't that the two frameworks contradict each other. The problem is that they describe different layers of reality without a way to connect them. Rethinking gravity means searching for a deeper principle that unifies these layers, a principle that might not resemble curvature or force at all. This search raises questions that were unthinkable in earlier eras. What if gravity isn't fundamental? What if it emerges from something more basic, information, entanglement, or interactions among components of space too small to measure? If gravity arises from collective behaviour rather than from a single underlying force, then the familiar description becomes a macroscopic illusion, like temperature or pressure. These concepts are real, but they emerge from the motion of countless particles. They don't exist at the level of single atoms. Gravity might follow a similar pattern. It might appear only when large numbers of microscopic interactions produce a smooth effect. If that's true, then the behaviour of gravity at cosmic scales or quantum scales could diverge significantly, because the collective behaviour changes in those regimes. Rethinking gravity requires being open to such possibilities, even when they challenge intuition. Another step in this re-examination involves considering whether additional forces might exist. Forces that mimic gravity in some situations but diverge in others. If a new interaction acts weakly, or only under extreme conditions, it could remain hidden for centuries. Yet its influence could explain anomalies without altering the familiar behaviour observed in everyday life. For example, a hidden force might strengthen attraction in galaxies while remaining insignificant near stars. It might influence the expansion of the universe without affecting local motion. The idea of a hidden force isn't an attempt to complicate the picture. It's an attempt to account for the behaviour that doesn't fit within the existing framework. Rethinking gravity means allowing for the possibility that nature contains more interactions than currently known. Another approach considers whether space itself contains properties not captured by traditional geometry. If the structure of space varies depending on density, curvature might not be the only way environments influence motion. Space might stretch differently in some regions and compress differently in others. These variations could act like a force, shaping motion without resembling anything familiar. In this setting, what appears as gravitational attraction might actually be a response to the dynamic properties of space. Rethinking gravity requires acknowledging that space could be active, not passive. Time adds another layer to this exploration. In Einstein's theory, time bends with space. It slows near mass and accelerates in emptier regions. But this might not be the full story. Time might respond to deeper principles that operate independently of curvature. If time flows differently in ways not captured by general relativity, then gravitational behaviour might reflect the relationship between these flows, rather than the shape of space. The idea isn't to discard curvature, it's to recognise that the influence of time on motion might be more complex than currently understood. Each of these possibilities, hidden forces, emergent gravity, active space, layered time, represents a path toward rethinking the fundamental influence that shapes motion. None of them eliminates the familiar gravitational effects. They simply explain them differently, placing them within a broader framework where the exceptions make sense rather than feeling like puzzles. Rethinking gravity means moving beyond equations that work into an understanding of why they work and when they stop working. The process doesn't end with reconciling anomalies. It extends into re-examining the assumptions embedded in the model. Gravity assumes objects respond to curvature. But what if motion arises from particles minimizing energy in a deeper field? What if inertia, acceleration, and paths are consequences of something that hasn't yet been defined? These questions matter because they open the possibility that the universe contains structure not visible through the current interpretive lens. Rethinking gravity invites questions that reach into the roots of physics, into the assumptions that were accepted because they worked, rather than because they reflected fundamental truth. Understanding what this means also involves recognizing that theories evolve not by destroying the past, but by expanding upon it. Newton wasn't wrong. His framework was incomplete. Einstein wasn't wrong either. His framework might also be incomplete. Rethinking Gravity acknowledges that the story isn't finished. It recognizes that the universe continues to offer behavior that doesn't fit neatly into the existing theory. Each anomaly becomes an invitation rather than an obstacle. This mindset shapes how the next breakthroughs might unfold. Instead of searching for a final theory, scientists may search for a framework that adapts to scale, context, and environment. Instead of expecting the same rules to apply uniformly, they may recognize that nature behaves differently under different conditions. Rethinking gravity means understanding that the universe doesn't follow human expectations. It follows its own structure, and the task is to uncover that structure rather than impose simplicity upon it. It also means being open to explanations that bridge physics, information theory, and cosmology. If gravity emerges from entanglement patterns, then understanding it requires understanding how information moves through the environment. If gravity reflects energy gradients in a deeper field, then the story of mass and motion becomes a story of interactions across scales. If gravity shifts depending on density, scale, or structure, then the picture becomes one where familiarity masks complexity. The implications of rethinking gravity reach beyond science. They touch the broader understanding of place within the cosmos. If the force that holds everything together is not what it seems, then the relationship to the universe changes. The environment isn't just a passive backdrop, it's a dynamic participant. The structures that seem stable are the result of ongoing interactions. The feeling of weight on the ground is not a simple downward pull, but a reflection of being embedded within a complex environment shaped by principles not yet fully understood. The idea isn't unsettling, it's liberating. It reveals that the universe is richer than earlier generations imagined. It shows that even the most familiar aspects of reality may hold secrets beneath their surface. Rethinking gravity becomes not an act of abandoning certainty, but an act of embracing curiosity. It invites the recognition that the universe is not static. The understanding of it shouldn't be either. As research continues, new data will arrive. Some ideas will fade, others will strengthen. The story of gravity will evolve, not because the universe changes, but because the ability to interpret it does. Each new insight will refine the picture. Each surprise will highlight where the next question should be asked. What it means to rethink the force that holds everything here is this: acknowledging that understanding is always provisional, recognizing that the universe continues to reveal layers beyond the ones already known, accepting that a familiar idea may be only one expression of something more profound, and embracing the possibility that the next explanation might reshape everything from the smallest particles to the entire cosmic landscape. Rethinking gravity is not about discarding the past, it's about making room for what comes next.